Alright, so this video is going to be covering the final for Spring 2024 of MA 162. Before I start, I want to say sorry if you saw my video on the second video or on the second exam for Spring 2024. I was gonna say just sorry about the crappy production quality on that video. I had to record that video with my phone because my stylus broke, and so I wasn't able to do a screen recording unless I was gonna use my hand as a pencil, I guess. Hopefully, despite the crappy production quality, hopefully that you were still able to get some good information out of that video. But yeah, but thankfully, yeah, for this one, I have my new stylus now, so I can properly make normal videos. But yeah, okay, cool. So yeah, so let's get into this. Let's get into this exam. Alright, so starting with the first question, we're given two series, and it's asking us to evaluate the behavior of the two series. And so, while going off the question, it's asking us to determine that whether it's absolutely convergent, conditionally convergent, or divergent. And so that tells us that we're going to be dealing with the case of two alternating series, but even if that wasn't mentioned, you can tell that we're dealing with alternating series here because of the fact that there's a negative 1 to the k power term attached to each of these series. And so as a result, the results that we could end up with are going to be a little bit more complicated than a normal case because we have to check for absolute convergence, conditional convergence, or divergence like the question says. And so I've written out a little flowchart here beforehand of the behavior of an alternating series. And so to start, what you want to do when you're dealing with an alternating series is first you want to just focus on the absolute value of your series and check for convergence of that. And so if the absolute value of your series converges, then that's going to be the most straightforward case. In that case, we can say that your series a sub k is going to converge absolutely. If that doesn't happen, then things are going to get a little more complicated. So let's just say the divergence case. The next thing you'd have to do is you'd need to check for these two conditions over here. You need to see if the limit of your series as k approaches infinity, you have to see if that goes to 0, and you also need to see if your series is decreasing. If both of those conditions are met, then you will end up with conditional convergence. Otherwise, your series is going to diverge. And so that's the general behavior of an alternating series. And so now we can apply those rules here. And so starting with the first series, we have just 10 to the k over k plus 10. Also, when you're handling an alternating series, you don't have to be sure not to include the negative 1 to the k term in your evaluation. That's just there to let you know that it's an alternating series, but you don't need to include it in your computations when you're doing like series tests and stuff. So taking the absolute value of the first series, also since we're taking an absolute value, it's going to cancel out the negative 1 anyway. So taking an absolute value of our first series, you'll end up with, let's just say, I'll just write it down here, we have 10 to the k over k to the 10th power. And to check for convergence of this series, I'm going to use a ratio test. I feel like that's going to be the most straightforward case. You might be thinking maybe we can use a root test because of the fact that we have a 10 to the k here, but even though you'll be able to nicely cancel out this k with a root test, you still have to deal with the denominator, and that's still going to be a little bit finicky. So as a result, yes, I'm going to use a ratio test for that. And so what that entails is you need to come up with another test series that takes the form of, let's just say, 10 to the k plus 1 over k plus 1 to the 10th power. And then what you're going to want to do is you're going to want to take the limits as k approaches infinity of the absolute value of our k plus 1 series, so 10 to the k plus 1 over k plus 1 to the 10th power over our original series of 10 to the k over k to the 10th. And then from here, with the ratio, what the ratio test entails is if this limit is less than 1, then it's going to converge. If it's greater than 1, then it's going to diverge. And if it's equal to 1, then it's going to be inconclusive. So hopefully we won't end up with the inconclusive case here. I have a feeling we won't. But yeah, so then we can simplify this limit a little bit, and this can turn into the limit as k approaches infinity of 10 to the k plus 1 over k plus 1 to the 10th power times k to the 10th over 10 to the k. And then these two 10s are going to cancel. And so then you'd end up with the limit of just 10 times k to the 10th over k plus 1 to the 10th. And then this limit is going to evaluate to 10, because if you're not sure why, if you don't remember why, what you'll realize is if you apply L'Hopital's rule a bunch of times onto these terms, the derivatives are eventually going to just turn into constants, where these k terms and then this k plus 1 term is eventually going to differentiate itself to 0, and all that you're going to have left is going to be 10. And so as a result, yeah, so the limit of this is going to be equal to 10, and that's going to be greater than 1, which means that we have divergence. And so as a result, we're going to have to check for conditional convergence as well. And so in order to do that, let's check the first condition. So we need to see if the limit of our series as k approaches infinity, we need to see if that's equal to 0. And so for that, we just have to take the limit, I'll just write it here, check for conditional convergence. We can take the limit as k approaches infinity of 10 to the k over k to the 10th power. And this limit is going to go to infinity. And the reason I know this is because so in the denominator we have a k to the 10th power. So if you apply L'Hopital's rule enough times, this is eventually going to differentiate itself into a constant. And then this term, if we take, let me do one pass of L'Hopital's rule and you'll see what I mean. So then this can turn into just 10 to the k to the 9th power. And then the derivative of 10 to the k, that's going to be the natural log of 10 times 10 to the k power. And so as you keep doing L'Hopital's rule, you can see here we have a natural log of 10. That's a constant. And so as you keep doing L'Hopital's rule, you're going to keep adding on these natural log of 10 terms. They're going to compound on top of each other, and at the end of that, you're still always going to end up with a 10 to the k term. No matter how many derivatives you take, this is never going to disappear. Whereas this term, that's eventually going to go to a constant. And so this is eventually going to simplify itself to, like, let's just say, I don't know, like ln of 10 to, like, I don't know, like the 10th power or something of times 10k over some constant. And so as a result, since this is just going to be some big fat constant, and so that doesn't really, it's going to become kind of insignificant as a result. And then this is also going to become a constant, and all that we have left is this k, and so it's just going to get bigger and bigger. And so this limit is going to go to infinity. And so as a result, we can see that our first series is going to diverge because of the fact that, well, we checked this limit and it went to infinity instead of 0. And so that's one of the conditions here not being met. We need both of these conditions to be met in order for conditional convergence to happen. So we don't even need to check to see if the series is decreasing. We can just say right away that this series is going to diverge. Now, moving on to the second series. The second series is going to be a little bit easier to deal with because we don't really have to do a ratio test to check for, to check for anything. Because what you'll see here is we can just use the rules of a p-series here, and we can use that to say that this series is going to diverge. Because we can see here, let me write it over here. Let's see. Yeah, let me write it over here. We can see here that this is going to be equal to 1 over k to the 1/2. And so from here you can see that p is going to be equal to 1/2, which is less than 1. And in order for a p-series to converge, your p-value has to be greater than 1, strictly greater than 1. But if it's less than or equal to 1, then it's going to diverge. And so we know right off the bat that the absolute value of this series is going to diverge. And so we can jump straight into checking for conditional convergence. And from here, the limit is also going to be simple. We can just say that we have the limit as k approaches infinity of 1 over root k. This is a bottom heavy fraction, so this is going to go to 0. And then also, since it's a bottom heavy fraction, we know that it's going to be decreasing, because if you use like test numbers, like if you just plug in numbers, the bigger your k value, you're always going to end up with a smaller number because it's just a 1 divided by whatever. And so from there you can deduce that right away that these two conditions are going to be met for the second series. The limit goes to 0, as well as the fact that we know it's decreasing. Now, if you're still not convinced, you can also take the derivative of this series, and you'll find that that derivative is going to be negative. And that's another way that you can see that it's indicative of the fact that it's a decreasing function. And so I can I'll write it out anyway. If you're not convinced, we can say that the derivative of 1 over root k, I forgot what that was off the top of my head, so let me just evaluate it real quick. That's going to be k to the negative 1/2, which is equal to negative 1/2 k to the negative 3/2. And so yeah, so we have a negative derivative, and so yeah, we can prove that way using that derivative that this series is decreasing, and then the limit is 0. And so the second series is going to be conditionally convergent. And so from here we can pick an answer choice. And so we can see here that since 1 is divergent and 2 is conditionally convergent, the answer is going to be B for this question. All right, so what is the radius of convergence of the given power series? So in this case, when you're dealing with, in most cases, when you're trying to find like a radius of convergence for a power series, it's going to be similar to the case of when you have a series that doesn't have like an additional variable in it, where except the only difference is you need to account for you have to do a couple of additional steps to ensure that there's going to be convergence. So similar to the case of a normal series, you can use the similar approaches, like the same approaches to determine which test you want to start with. So in this case here, we can see that this term goes to the k power as well as this term. And so that screams to me root test. Using the root test here is going to be the most straightforward case. And what that entails is just taking the limits as k approaches infinity of the kth root of whatever given series a sub k. And then similar to the ratio test, if that limit is less than 1, then it's going to converge. If it's greater than 1, then it's going to diverge. And if it's equal to 1, then it's going to be inconclusive. And so applying those rules to this series, if we take the square, the kth root of this series, you'll end up with something that takes the form of, let's just say, the limit as k approaches infinity of the kth root of 1 plus 2 over k to the k power times x to the k. And then this is going to simplify to just 1 plus 2 over k times x. And then evaluating this limit, we have the only k term we have is here, and so that's a bottom heavy fraction, and so this limit is just going to turn into 1 plus 2 over infinity times x, which just equals 1 plus 0 times x, and then that just simplifies to x. And so from here, since we used a root test to get here, we need to figure out a value for x that guarantees convergence, and we know that a root test converges when the limit is less than 1. So we need something that's strictly not equal to, not less than or equal to, it has to be strictly less than 1. And so x has to be less than 1. And the cool thing is, for this series, there aren't any other conditions we have to look for, because as long as x is less than 1, this series is always going to converge. You can pick whatever number you want. You can use, I don't know, you can use maybe something like, you can use like negative 9,000 or something. That's going to be less than 1. As long as it's less than 1, it's going to converge. And since there's no other conditions we have to look for, we can just say that the radius of convergence is simply just going to be 1. And so the answer to this question is going to be A. Okay, so what are the first three terms of the Maclaurin series for f of x is equal to the square root of 1 plus x? So to start, before I start anything, let me write out what we're going to be using. So recall that a Maclaurin series, that's a special case of a Taylor series, where the only difference between a Taylor series and a Maclaurin series is a Maclaurin series is just going to be a Taylor series centered at 0. So to start, let me write out what the formula for a Taylor series is, and then go from there. So we know that if you were to use a Taylor series onto a function, we can say that f of x is going to be equal to the infinite sum from n is equal to 0 to infinity of the nth derivative of f evaluated at a over n factorial times x minus a to the n power. And I mentioned that a Maclaurin series is going to be a Taylor series centered at 0. And so what that means is that's just a case where a is equal to 0. So that's just a case where a is equal to 0. And so that's just going to simplify the formula to just f of x is going to be equal to the infinite sum from n is equal to 0 to infinity of the nth derivative of n evaluated at 0 over n factorial times x to the nth power. And then from here, all we have to do is come up with the first three terms. So applying that formula, you should end up with a equation that takes the form of since we're starting at n is equal to 0, our first term is going to be the 0th derivative because we're dealing with the nth derivative over 0 factorial. So let me just write it out. So you should end up with since it's the 0th derivative, that's just the original function. And so that's just going to be oops, I didn't mean to do that. Oh crap, let's see, where did we go? Oh, there we go. Okay, cool. So yeah, so starting with the first term, you should end up with just f of 0 over 0 factorial times x of 0. And then you're going to add from there the first derivative, so f prime of 0, since that's n is equal to 1, over 1 factorial times x to the first power plus f double prime of 0 over 2 factorial times x to the second power. And then with that, all we have to do is just plug and chug, and we'll have our answer for this question. So starting with the first term, we can write this out as just, since we know that f of x is equal to the square root of 1 plus x, that's just going to be the square root of 1 plus 0, which is just 1. And then 0 factorial, that's going to evaluate to 1. And so this is going to become a 1. And then x to the 0th power is also going to be a 1, so this is just going to become 1. And then for the second term, we have to take the derivative of f of x, so let me write that over here. So we know that f of x is equal to the square root of 1 plus x. And then taking that derivative, we can say that f prime of x is going to be equal to 1 over 2 times the square root of 1 plus x. And then the second derivative, that's going to be equal to, I'm going to first rewrite this as 1/2 times 1 plus x to the negative 1/2 power. It'll make it easier to find the second derivative, because from there you can just use power rule without having to move things around between the numerator and denominator. And so that's going to give you 1/2 times negative 1/2 times parentheses 1 plus x to the negative 3/2 power. And then that can simplify to just negative 1/4 times 1 plus x to the negative 3/2 power. So now that we have those derivatives, we can plug those back into our original equation. And so f prime of 0, that's going to just be equal to 1/2 times 1 plus 0 to the negative 1/2 over 1 factorial, which is going to be 1, and then x to the first power, that's just going to be x. And then our final term, we're going to end up with, so putting a plus there and then plus, we're going to end up with negative 1/4 over 1 times 1 plus 0 to the negative 3/2 over 2 factorial. 2 factorial, that's equal to 2 times 1, and so that's going to be equal to 2. And then we have an x to the second power, so that's just going to simplify to x squared. And then we can simplify this, so the first term, that's just going to become 1, because it's just a bunch of 1s. So you end up with 1, and then we end up with 1 plus 0 is 0, and 1 to the any power is still 1, so you just end up with 1/2 divided by 1, so this is going to simplify to 1/2 times x. And then the last term, that's also a similar case where we just have 1 plus 0, that equals 1, and then 1 to any power is still 1, so that simplifies to just negative 1/4 divided by 2, which is going to simplify to negative 1/8. And so you'll end up with just minus 1/8 times x squared. And then matching that up with our answer choices, we can rewrite this as that's just going to be equal to 1 plus x over 2 minus x squared over 8. And so matching that up with our answer choices, that matches up the closest with answer choice B. So the answer to this question is going to be B. Alright, so this question is asking us to evaluate the following series, and it also gives us a very important hint. It's telling us to use the Maclaurin series for arctangent of x to get somewhere. That hint is very important, and you should actually take note of that hint, because if you look closely, you'll come to realize that this series actually takes up a form that's very similar to the Maclaurin series for arctangent of x. So let me write that up here real quick. We know that arctangent of x, when you convert that to a Maclaurin series, that's going to be equal to what is it again? Oh, wait, I forgot. That's going to be equal to the sum of n is equal to 0 to infinity. That's not an infinity. To infinity of -1 to the n power times x to the 2n plus 1 over 2n plus 1. And so from here, then we have to equate it to this. And then so from here, we'd have to equate equate this with our original series. So we can say that this would be equal to -1 to the n times x to the 2n plus 1 over 2n plus 1. And so then we'd have to manipulate this equality here to make sure that this would be true. And so the first thing I'm going to do is I'm going to isolate things. Notice how in both our original series as well as this, we have a 2n plus 1 term. And so you can go from here and isolate the 2n plus 1 and end up with something that looks like 1 over -3 to the n power times 1 over 2n plus 1. And then that's going to be equal to -1 over n times x to the 2n plus 1, which is going to be equal to 1 over 2n plus 1. And then from here, now that we've isolated, you can see now that since we've isolated that 1 over 2n plus 1, we can just cancel these out, and you just end up with a more simple expression that just looks like 1 over -3n is going to be equal to -1 to the n power times x to the 2n plus 1. And then to isolate that x to the 2n plus 1 power again, we can just move this to the other side, and you'd end up with x to the 2n plus 1 is going to be equal to 1 over -3 to the n times -1 to the n, which is going to simplify to 1 over -3 times -1 over n, which is just going to simplify to 1 over 3 to the n. And so then you can say that x to the 2n plus 1, that's going to be equal to 1 over 3 to the n. And now you might be thinking from here, then we can just solve for x, and you'd end up with like x is equal to the 2n plus 1th root of 1 over 3n, but I'm actually not going to do that. The reason why I don't want to do that is because this value is not very useful to us, because since we're using the Maclaurin series for arctangent of x, we want to come up with an x value that we can just plug back into arctangent of x, and then that would give us an answer. That'll make sense in a second, or at least I'll try to make it make more sense. This question is probably, I'd say this is probably the hardest question on this exam. Yeah. And so instead what I'm going to do is we're going to have to do a little bit of guessing and checking, or make an educated guess, and come up with like a test value for x in this equation that still makes it so that x, so like our test value for x would take up a form that's similar to this 1 over 3n. And so what I mean by that is, in this case, I'm going to use a test value of, let's just say x is equal to 1 over the square root of 3. And the reason why I'm going to use that, you'll see why in a second. When you plug this back into this expression, you end up with 1 over the square root of 3 times, to the 2n plus 1 power, and then that's going to equal, that's just going to equal 1 over the square root of 3 to the 2n plus 1. Since this is just a 1, it's just going to simplify to 1, and then that's going to further simplify to, this can further simplify to the square root of 3 times 2, or no, it can be expanded to the square root of 3 to the 2n power times the square root of 3, which can then be simplified to 1 over 3n root 3. And so now you can see, while this is not exactly equal to this, you can see that it's very close. We can see that this is like, it's very close to that. Because this is, and so, how should I put it? I'm trying to figure out how I can put that, how I can put this. Since this is very close, to this, what we can do from here is just isolate a 1 over root 3 multiplied by 1 over 3n, and then we can plug this back into our original Maclaurin series here, and then solve this problem. Now, and so when you do that, you should end up with an expression that looks like this. So you'd end up with like you'd end up with something that looks like this infinite sum of n is equal to 0 to infinity of -1 to the n times 1 over the square root of 3 to the 2n plus 1 power over 2n plus 1. And the next thing we're going to have to do is also, since I mentioned that this is very close to this, because we wanted something that's close to that, but it's not exactly close, the way that you would make this be exactly equal to this is by multiplying it by the square root of 3. And so because then it would cancel out with the square root of 3 in the denominator, and then it would just end up being back to being equal to this. And so similarly, you'd also have to multiply this entire series by the square root of 3. And when you do that, after doing that, those mental gymnastics, believe it or not, this is actually going to be equal to our original sequence over here. And so now what we've effectively managed to do is we've managed to convert this original series into something that looks like the Maclaurin series for the arctangent of x. And since we know that this without the square root of 3 outside, since we know that's going to be the Maclaurin series of arctangent of x, we can say that that's actually going to be equal to what is it? Oh yeah, we can say that this is actually going to be equal to the square root of 3 times arctangent of 1 over the square root of 3. And then from here, it's just a matter of simplifying this expression, and you'd end up with an answer. And so when you do that, we know that recall that the arctangent of 1 over root 3, that's going to evaluate to pi over 6. So you'd end up with a square root of 3 times pi over 6. And so then you can simplify this, and it's ultimately going to be equal to the square root of 3 times pi over 6, like so. And then that would be the final answer to this question. Yeah, and so matching that up with your answer choices, you should end up with A. I hope that did make sense, because this, yeah, I'd say after looking at all the questions on this exam, I think this one was definitely the most tricky one. But yeah, so after doing those mental gymnastics, the answer to this question would be A. All right, so in this question, we're given two vectors v and w in 3 dimensions that satisfy that the dot product between v and w is equal to -3, and the cross product between v and w is equal to a new vector of 1, -2, and 2. So what is the angle between v and w? So to start, let me draw this out so we know what we're dealing with visually. So we have two vectors v and w like this, and it's asking us to find the angle, which I'll denote as theta. And so when you're dealing with problems like this, when you're dealing with like vectors and angles and dot products and cross products and stuff, there's a couple of formulas that you can work with that relate the two together. That relate trigonometric functions and angles and stuff with vectors, dot products, and cross products and stuff. And so to start, we know one of the first formula, we can say that sine of theta, we know that that's going to be equal to the magnitude of the cross product between v and w. I'm using v and w because those are the vectors given to us, so I'm going to use those as the variables for these equations as well, over the magnitude of v times the magnitude of w. And then cosine of theta, we know that that's going to be equal to the dot product between v and w over the magnitude of v times the magnitude of w. And usually with these formulas on its own, you can use these plug-in stuff and solve for theta, and you'd have an answer. The problem with this question, though, is it tells us what the dot product and cross product of the two vectors are equal to, but we don't know what the individual vectors are beforehand. And so as a result, in order to find the magnitude of these vectors individually, like in these formulas, we'd need to know what the vectors were equal to originally, which we don't. And so we have a case of unknowns that we have to get rid of since we're trying to solve for theta. And so on its own, we can't do anything with these formulas. But the way to deal with this question is I'm also going to introduce tangent into the mix, and then it'll make this question solvable. So we know originally that tangent of theta, if you recall, that's equal to sine of theta over cosine of theta. And since we know that sine of theta and cosine of theta are equal to these things, we can say that tangent of theta is going to be equal to the magnitude of v crossed with w over the magnitude of v times the magnitude of w divided by v dotted with w over the magnitude of v times the magnitude of w. And then from here, this can simplify, and with some cross multiplication, this will turn into, actually, let me write it down here. This can simplify to v cross w magnitude over v, magnitude v times magnitude w times magnitude v magnitude w over v dotted with w. And then from here, these can cancel, and then we just end up with where tangent of theta is going to be equal to v crossed with w, the magnitude of that, over v dotted with w. And so now we've came up with a relationship that gets rid of all the unknowns, and then from there we can just solve for theta. So let me write that down here. So we can ultimately say that tangent of theta is going to be equal to v cross w over v dotted w. And the cool thing is we do know what the dot product and cross product are equal to. And so from here, all we have to do is plug and chug. And so to start, let's plug those things in. So this is going to be equal to the vector of 1, -2, and 2 over -3. And since we're taking a magnitude, recall that a magnitude of this, that would just be equal to the square root of it's going to be the square root of each of the terms of the vectors squared added together. So that would look like 1 squared plus -2 squared plus 2 squared in a square root over -3. And that magnitude calculation is going to allow us to turn our vector into a scalar. And so then this would be equal to just 3 over -3, which equals -1. And so now we can say, moving back up here, moving back up here, we can say that tangent of theta is equal to -1. And then from here, we just have to take the tangent inverse and we'll have theta. And so since tangent of theta is -1, then we can say that theta is equal to the tangent inverse of -1. And if you remember the properties of your unit circle, you'll find that theta is going to be equal to 3 pi over 4. And this is going to be the angle between these two vectors. And so, yeah, so as a result, the answer to this question is going to be D. Okay, so in this question, we're dealing with a solid that has a semicircular base of radius 2. And the cross sections perpendicular to the base and parallel to the straight edge of the semicircle are squares. So what is the volume of the solid? So before I do anything for this question, the first thing I'm going to do is I'm going to graph out a top-down view of our solid. So a top-down view of the base of this solid. So you'd end up with a graph like an XY plane that looks like this, where you have a semicircle that looks a little something like a semicircle that looks a little something like this, with this being the x-axis and this being the y-axis. And then we know that the radius of the semicircle is going to be 2, so I'll link that as well. So we're going to have like 2 units going up on the y-axis. And then we know that, and then the next thing it tells us is that we know that the cross sections for the semicircle are going to be parallel to the straight edge of the semicircle and perpendicular to the base. And so you can see that in this, oops, let me get rid of that. You can see that in the drawing here. You can see how the cross sections are in fact perpendicular to the base. So I just put a right angle there to show that. And then we know that the cross-sectional areas are going to be parallel to the straight edge, so that would look like something like this, where if you were to look at the cross-sections from the top down, you'd end up with a bunch of lines that look like this. And then the next thing I'm going to do is now, from here, we can start to bring out the function, or no, the equation we're going to use to calculate volume. So recall that when we're trying to find the volume of a solid like this, we know that we're going to have to use some sort of integral formula. And that's going to take the form of this, where we know that V is going to be equal to the integral from A to B of some cross-sectional area. And then to determine which variable you want to integrate with respect to, what you'll notice here is well, our choices would be x and y. You want to integrate with respect to the variable that's perpendicular to your cross-sectional areas. So we know that the cross-sectional areas are parallel to the straight edge, which is parallel to the x-axis. And so that would make the y-axis perpendicular to our cross-sections, as you can see here. So we're going to want to integrate this with respect to y. And then the next thing we have to do is we need to come up with a function that represents the area of the cross-section, and then integrate that. And so for that, we know that the cross-sectional area is going to be a square. So if I put in a head-on view of our cross-sectional area, we have a square here. And we know that with a square, the length of each side is going to be the same. So we can just use the same letter to represent the length on each side. So I'll just use S. So S, 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 and S. And then we know that to find the area of a square, that's just going to be base times height. So the area would just be equal to S times S, which would just equal S squared. And then we can plug that into our volume formula. We can say that V is going to be equal to the integral from A to B of just S squared with respect to Y. Now we're integrating with respect to Y, but we have this S in here, and we don't know what that is. So we also have to come up with what S actually is going to be, because we don't know what the length of our cross section is going to be. We just know that the area is going to take a form of S squared, but now we have to figure out what S actually is. And the next thing I'm going to bring in for that is, to get to that, we're going to have to use, since we're dealing with a semicircular base, we're going to also have to use a function that represents a circle and get closer to that. And so to summarize, basically, we're going to be putting a function inside of a function and then integrating that, and that will give you a volume. So the next thing we have to do is, we know that we're dealing with a circle. And we know that the general function that represents the circle is like x squared plus y squared is equal to like some radius squared, right? And we know in this case that the radius is going to be 2. So in this case, the function that represents a circle in this case would be x squared plus y squared is going to be equal to 4. And then the next thing we have to do is, since our integral is going to be with respect to y, we're going to have to turn this function into something where x is isolated. And so when you do that, you'd end up with like x is going to be equal to plus or minus the square root of 4 minus y squared. Now, since we're dealing with a semicircle, I put this plus or minus in front of the term because that's technically correct, but that's for if we were dealing with a full circle. Since we're dealing with a semicircle, we're only going to have to deal with either the plus case of the square root or the minus case. So for the sake of making the calculation easier, I'll just use the plus case. And so we can simplify x to just be equal to this. So x is equal to just the square root of 4 minus y squared. Now there is one more thing that we have to do, because the problem with this function, x is equal to the square root of 4 minus y squared, is if you were to graph this onto our top-down view, you're going to end up with a semicircle or a curve that looks like this. And so it looks like this instead of what we want, that being this. And so what we're going to have to do, and so in its current form, that x is only going to compensate for half of the length of the cross-sectional area. And so we're going to have to double that, and that would give us the full length to compensate for the fact that it's only covering half the length, like I showed earlier, so like this over here. And so in order to do that, what you would have to do is we just have to double x. And so from that, you can deduce that the length s is going to end up being equal to 2 times x instead of just x. And then we can plug that into our volume formula. So we can say that this is going to be equal to the integral from a to b of 2x squared. And then we know that x is going to be equal to the square root of 4 minus y squared. So our volume formula is ultimately going to be equal to the integral of 2 times the square root of 4 minus y squared, like so, with respect to y. And then all we have to do from here is figure out what our integrating boundaries are going to be. And for that, that's not going to be too bad. I mentioned that we're integrating with respect to y because that's perpendicular to the cross-sectional area. And so our lower boundary, that's just going to be the x-axis, because we can see that the semicircle ends there. And then we can see that we know that the radius of our semicircle is 2, which would mean that the y-intercept of our semicircle is here at 2. And so that would make the upper boundary 2. And so the integral boundaries for our integral are going to end up being just 0 and 2. And so now we have a function that's fully set up, and all we have to do from here is just integrate this and spit out an answer, and we'll have an answer for this question. So first, I'll simplify this a little bit, and this can simplify to the integral from 0 to 2 of 4 times 4 minus y squared with respect to y, which is going to be equal to, that's going to be equal to the integral from 0 to 2 of 16 minus 4y squared with respect to y. And so that's a pretty simple integral. That's going to end up just evaluating to, just 16y minus 4y cubed over 3, evaluated from 0 to 2. And then when you plug in those boundaries, you'll end up with just 16 times 2 minus 4 times 2 cubed over 3. And then for the lower boundary, that's just 0. So when you plug that in, you'll just end up with a bunch of zeros. So we can just keep it as simple as this. And then when you simplify this, you should end up with 32 minus 2 cubed is 8. 8 times 4 is 32, so minus 32 over 3. And then when you simplify this, this is just going to go to, that's just going to go to 96 over 3 minus 32 over 3, which is ultimately going to be equal to 64 over 3. Oops, let me get rid of that as well. Okay, yeah, there we go. So now we have, so now we have the, and then let me clean up that box too. So now we have something that represents the volume, so 64 over 3. And so this would be your final answer to the volume of this. And so now all we have to do is just match this up with our answer choices. And so you can see from here that matching that up with our answer choices, the answer to this question is going to be E. Alright, which of the following shows the graph of the polar curve r is equal to cosine of theta plus sine of theta relative to the coordinate axis? So this question is asking us how well we understand how to graph polar curves. And so I've conveniently written out a table as well as part of the unit circle, because that's what's going to be useful for questions like this. I'd say just in general, when it comes to polar coordinates, you have to have a strong understanding of the unit circle and stuff like that to properly understand how it works. And recall that with polar coordinates, unlike Cartesian coordinates, you have like I guess everything is like, everything behaves like some sort of like radial operation or like an orbital or something. And we know that in the case of polar coordinates, our two variables are going to be r and theta. And recall that r, that's going to represent the distance from the origin. So, and then theta is going to represent the angle. So like, let's say we had like a theta angle of 0 and an r value of like 4 or something, then you'd end up with maybe like a term somewhere around here or something, where it's like 4 units away from the origin and the angle is 0, so it ends up like on what would be the Cartesian x-axis. And then I've also written out the angles that we're going to need to use to graph this. In terms of graphing a function, it's similar to when you learn how to graph Cartesian functions at the very beginning back in like middle school or something, except it's just that the graph behaves a little differently, where you just plug in like test values that I've written over here, and then it spits out an r value, and then you just connect the dots, and you have a graph. So starting with the first case of theta is equal to 0, plugging that into our function, we end up with cosine of 0 plus sine of 0 is going to be equal to 1 plus 0, which just equals 1. And so since our r value is equal to 1, that's going to give us like, that's going to be equal to 1 unit away from the origin. So let's say that's like maybe like somewhere around here or something. And then for our next case, we have pi over 6. So rinse and repeat the same process. Cosine of pi over 6 plus sine of pi over 6 is equal to root 3 over 2 plus 1/2. And you don't have to remember exactly what this is equal to. The most important thing is this is going to be greater than 1, though. This is approximate, I think if I recall correctly, that's equal to like 1.37 or something. So, but the important thing is the fact that it's bigger than 1. And so that means, like, going back to our x-axis here, we have our new pi over 6 is going to be 1.37 units away from the origin. So it's going to be a little bit further from the origin than this current purple point. But since this is at the angle of theta is equal to pi over 6, we're going to shift it up to this line over here. And so our point is going to end up like somewhere around here, like so. And then the next thing we have to do is just move it, and then just keep rinsing and repeating that process. And so yeah, so now at this point, I'll just plug in the numbers rather than plugging it into the function. So you'd end up, in the case of pi over 4, you just end up with root 2 over 2 plus root 2 over 2, which once again is bigger than 1.37, which is our previous value. That's approximately equal to like what, 1.41, I think. So similar to the first case, that's going to be like 1.41 units away from the origin. So somewhere around like here or something, and then we're going to shift up to our angle of pi over 4. So our point's going to end up somewhere along this line. So you'd end up with like a circle here, like a dot here. And in the case of pi over 3, we end up with 1/2 plus root 3 over 2, which equals 1.37 again, but it's going to be less than 1.41. So now we're getting closer to the origin again. So we're going to end up like somewhere around like here, and then shifting up to pi over 3, we end up on this line somewhere around like here maybe. And so then you'd end up with a dot like here. Now for pi over 2, you end up with 0 plus 1, which just equals 1. So now it's going to be 1 unit away from the origin, but it's going to be on what would be the Cartesian y-axis. So you'd end up with like a dot here. And then moving on to 2 pi over 3, you end up with negative 1/2 plus root 3 over 2, which once again is going to be less than 1. That's approximately equal to like, I think, like 0.37, I think, something like that. And so now we're along this line. Now we're along this line being 0.37 units away from the origin. And so that's going to result in a dot that ends up like somewhere around here. And then moving on to the next point, we have 3 pi over 4. So we're going to be along this line, and that ends up being just negative root 2 over 2 plus root 2 over 2. That's going to be equal to 0. And so since it's equal to 0, that's just going to be the origin. So we're going to end up with a dot right on the origin, like so. Now for 5 pi over 6 in pi, this is where things are going to start to get interesting. Because now that we're on the line of 5 pi over 6, this side is going to be the positive direction. Because we've shifted, like starting from here, we've went all the way over here, if that makes sense. So that's why like the positive direction has rotated a little bit. And so now this side of the axis is going to be a negative. And so when you plug in the numbers, you end up with negative root 3 over 2 plus 1/2, which is going to give you approximately equal to like what? Negative 0.87, I think. And so since we have a negative number, we have to go a distance in the opposite direction of our positive line. And so you're going to end up with like a dot like somewhere around like here or something. And then finally for the last case, it's the same process where you just end up with negative 1 plus 0, which equals negative 1. But since we've rotated our positive axis, our positive axis started over here, and we rotated it all the way over to this side. So now in the case of pi, this is going to be the positive side, and this is going to be the negative side. And so since we have a negative 1, we're going to end up with a dot back where we started, which that being this point here. And so we've completed the graph pretty much. At this point, going any further, you're gonna end up repeating this circle over and over again. So once you connect the dots, you should end up with something that looks like this. I know this doesn't look like a circle, but I hope you can kind of see like the point that I'm getting across here. And so matching up this that really crappy drawing with the answer choices, you can see that this is going to match up the closest with answer choice B. So yeah, so the answer to this question is going to be B. Okay, find the value of a if the integral from 0 to pi over 2 of e to the 2t times sine of t with respect to t is equal to a plus the integral from 0 to pi over 2 of 2 times e to the 2t cosine of t with respect to t. So just looking at this question right away, I know that this is going to be a case of dealing with some sort of integration by parts. And for one, it's because, well, looking at this integral here, we have two separate parts that are of completely different forms of each other from each other. Like we have like a trig expression and an exponential expression here. And so we're going to have to treat those as two separate entities. And then also what you'll notice is that this expression actually resembles the general formula for integration by parts. And so I'll write that over here. So we recall that the general formula for integration by parts is equal to the integral of u dv is equal to u times v minus the integral of v du. And then another step that we have to look out for, since we're dealing with a definite integral, the formula for integration by parts also changes with that. So plugging in our boundaries, we'd have a to b here, a to b here, and then we'd also have where we'd have to evaluate u and uv from a to b. This is a very important step over here, because unlike other integration techniques where you just do the integral and then plug in the boundaries at the end, with integration by parts, every time you come up with a uv term, you have to evaluate each of those individual uv terms' boundaries on its own. If you don't do that, you could end up with the wrong answer. You won't always end up with the wrong answer, but you could. And so be sure to look out for that, because that can trip up a lot of people. And also what you'll notice is in the answer choices, they're all constants. There's not any variables in them. And so that proves what I'm talking about, where our hypothetical A had these boundaries plugged into it. And that's why our final answer is going to be some sort of constant. And then also, if you're not sure where the integration by parts formula comes from, if you're curious, you can derive that from the derivative product rule, because that's what integration by parts is. It's kind of the integral counterpart to the derivative product rule. Yeah. And then another thing is usually from here, from here, all we have to do is come up with a u, a du, a dv, and a v term. And usually in most cases, oftentimes you'll have one part that differentiates to 0 eventually, and another part that just does its own thing, and that makes the process of picking your u's and v's pretty simple. If you have like a part that where both parts are differentiable or integrable, then pick the part. Then it would be the most straightforward case to just pick the part that eventually differentiates itself to 0. But when you're dealing with a case like this, where both of these terms, they'll never turn into 0 no matter what you do to them, you'd have to follow a different rule, that being the I late rule, or however you want to call it, where you just have this acronym that stands for I would be inverse trig, and then L would be logarithms, any sort of logarithms, and then A would be anything algebraic, and then T would just be trig, so just regular trig, and then E would be exponential. And going from top to bottom, that's the priorities of that'll help you to prioritize what to set for U. Now, in this question in particular, because of if we were to use this acronym to pick our U term, then we'd end up picking sine of t as our U term. But for this question, I'm actually not going to do that. And the reason why is because this expression has a plus here, whereas our general formula for integration by parts has a minus here. And so I want to pick something for my dv that turns into a negative when I integrate it, and that'll allow our expression here to turn into something that looks more like this. So usually I would follow this procedure. But in a case like this, where you have an exponential as well as just a trigonometric, you can kind of break the rules a little bit and not follow it. And so I'm actually going to do that for this question and set u equal to sine of, I'm going to set u equal to, I'm going to set it equal to e to the 2t. And then I'm going to set dv equal to sine of t. And now when I come up with our du's and v's, you'll be able to see why I broke the rules here. And so integrating dv to get v, you end up with negative cosine of t. And also you got to keep a dt here as well. And then when you differentiate e to the 2t, you end up with 2 times e to the 2t. And so now you can see we have two terms here that match up with this part of the equation. And so that's why I broke the rules of this for this question in particular. And so when you plug everything in, you'll end up with something that takes the form of u times v, so that's going to be e to the 2t times negative cosine of t, plus, instead of minus, because we have a negative here, plus from 0 to pi over 2 of cosine of t times 2e to the 2t dt. And then also let me rearrange this so that it looks exactly like our given expression. So e to the 2t like this times cosine of t. So now you can, oh, and then also I have to, don't forget, evaluating the boundaries for each uv term. So now that I've written it like this, you can clearly see how this expression is going to take the form of this. And to find a, all we have to do is just evaluate this. We don't even have to compute this entire integral. We just have to figure out what this is. And so when we do that, you should end up with an expression of just e of 2 times pi over 2 times negative cosine of pi over 2 minus e to the 2 times 0 times negative cosine of 0. And then this can simplify to just e to the 1, and then cosine of pi over 2 is 0, so that's going to become 0, and then we end up with, or no, wait, no, this is e to the pi. I mean, it doesn't matter because that's going to go to 0 anyway. I just want to keep things consistent. And then this that's e to the 0, so that's just going to turn into 1, and then cosine of 0 is equal to 1. And since we're dealing with a negative one, since we're dealing with a negative here, this negative here, it's going to turn into negative 1. And so this is ultimately going to simplify to just 0 plus 1, which equals 1. So the answer to this question, or yeah, so then we can see that that would be the value of a that we're asking for. And so the answer to this question is going to be E. Oh, and then also another thing, if you saw my video for the second midterm for spring 2024, I mentioned an alternate approach to integration by parts of using the tabular method. If you saw that, if you remember, for this question, it wouldn't really be helpful here because neither of the terms differentiate to 0. I just wanted to point that out. But so the answer to this question is going to be E. So if the given power series converges at x is equal to negative 1 and diverges at x is equal to 4, then what can be said about its radius of convergence, r? So to start, I want to put emphasis on the fact that it's asking about the radius of convergence rather than the interval of convergence, because that's going to make a big difference in what we come up with for our answer. So yeah, so I want to make it clear we're figuring out a radius of convergence, not an interval of convergence. So anyway, now with that out of the way, we know that we're dealing with a power series because, well, the question says so, but also because this series takes up the form of a power series because of this term on the right, that x minus 1 to the k power. That's what makes it a power series. And one thing to note with power series is that we know that, let's just say we have like a series, I don't know, like where you have a term of like x minus a to the k power. With a power series, we know that it's, at the very least, regardless of like its interval of convergence, we know that it's guaranteed to converge when x is equal to a. And in this case, a is going to be equal to 1. So we know that a power series is always going to converge at x is equal to 1 in our case. At the very least, we know that it's going to converge at 1. You could have a situation where it doesn't converge anywhere else, but we know at the very least it's going to converge at x is equal to 1. So now I'm going to plot this onto a number line, and I'm going to use that x is equal to 1 value as our baseline, because that baseline is going to allow us to come up with a range of what the radius of convergence r could be. You can see in these answer choices here too, it's like, for example, like with answer choice A, that's saying that r could be anywhere between 2 and 3. And so now what we have to do is we need to measure the distance from our baseline of x is equal to 1, the distance from that to these values of x is equal to negative 1 and x is equal to 4. So plotting those two numbers on our number line, you end up with negative 1 here, and you end up with 4 here. And the distance between those two numbers is going to be 2 units and 3 units. And if you're not sure how I got that, you can just take the absolute value of the difference between the two numbers. So with the case of x is equal to negative 1, taking that absolute value, you end up with the absolute value of negative 2, which is equals 2. And then x is equal to 4, you do the same process of 4 minus 1 equals the absolute value of 3, which equals 3. And so now that we know that the distance from our baseline to the convergence and divergence points given to us is going to be 2 and 3, our radius of convergence, the numbers that it could be, is going to be dependent on the distances to these points, rather than these points. If we were dealing with an interval of convergence, then the interval of convergence would deal with these points. But we're dealing with a radius of convergence, so we have to ignore these points and focus on these 2 points. And so, since we know that the distance from our baseline to negative 1 is 2 units, we know at the very least our radius of convergence is going to be at least 2. So putting that over here, we just end up with a 2 is less than or equal to r. And then in the case of from 1 to 4, we know that the distance from 1 to 4 is 3. And so that means that our radius of convergence is going to be at most 3 units. And also, another thing to note here is in this question, the fact that that it tells us it converges here and diverges here isn't as important because we're not dealing with an interval of convergence. I mostly want to focus on what these values actually are. And so um, so to conclude, to summarize this entire thing, after summing this all up, we know that our radius of convergence for this series could be anywhere between 2 and 3, inclusive. Um, since we're dealing with a radius of convergence, that's why I put a less than or equal to here rather than a like a less than or something. Because I know sometimes when you're coming up with an interval of convergence, you could end up with like a situation of like an answer choice that looks like D, but that's actually going to be a beta answer, and so it's not going to be D in this case, even though it says that it diverges at x is equal to 4. And so yeah, so matching that up with our answer choices, the answer to this question is going to be A. Okay, convert the polar coordinates of 4 and 7 pi over 2 to Cartesian coordinates. So for questions like this, there's a couple of ways that you can approach it to get an answer. The more straightforward way would just be to take a formulaic approach where you just use the conversion formulas between Cartesian and polar. But if that doesn't make sense to you, there is a way that you can visualize these kind of questions and get an answer that way. Since the formulaic approach is going to be the more straightforward approach, I'll start with that and then show the alternate approach later. And then since we're dealing with polar coordinates here, we know that instead of x and y, you're going to be dealing with r and theta. So this would be r, and then this would be theta. And then converting this back to Cartesian, we can use the conversion formulas where we know that x is going to be equal to r cosine of theta, and y is going to be equal to r sine of theta. And so then from there, you just have to plug in the numbers given to us, and you'll end up with an x and y, and then you can pick an answer. So starting with x, we can say that x would be equal to 4 cosine of 7 pi over 2, and then y would be equal to 4 sine of 7 pi over 2. And in the case of theta, we know that theta is a multiple of pi over 2. So cosine of any multiple of pi over 2, that's just going to go to 0. So x is just going to end up being 4 times 0, which just equals 0. And then in the case of sine, when you're dealing with sine of any multiple of pi over 2, that'll either give you a positive 1 or a negative 1. In this case, you'll end up with just negative 1, so 4 times negative 1, and then that's going to give you negative 4. And then plugging those into our new points, you'd end up with just x is equal to 0, and then y is equal to negative 4. And so matching that up with the answer choices, you'd end up with answer choice D. Now, if that doesn't make sense to you, you can also visualize this by drawing like a bare bones unit circle and going from there. But if this formulaic approach makes sense to you, then you can move on from this question. But I'll show that this approach might be a little more intuitive for some people, where you just draw a super bare bones unit circle. You don't have to draw out all of the points of it. For this question, we're only going to need the points here, 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 and here. And so drawing that out, we know that here on a unit circle, that would be equal to 0, and then pi over 2, and then pi, and then 3 pi over 2. And then making a full circle, you'd end up back at 2 pi. So a full rotation would be 2 pi, and that's why in polar coordinates, a full circle around theta is also 2 pi. And so looking at that, you can see here that, well, if you do a full rotation, to start, well, before I do anything else, let me start with the way polar coordinates work as opposed to Cartesian, if you don't remember. We know that r is going to be the distance from the origin. So in the case of here, we have an r value that's equal to 4. That would be like 4 units away from, like if we had a point here, then r would be like, this would be like 4 or something. So 4 units away from the origin. And then theta, that just represents the angle around this plane. And so r is just going to be a straight line going out away from the origin, and then theta is just the angle of that point, if that makes sense. So going back to theta, we have 7 pi over 2, and we know that since it's a multiple of pi over 2, our point's going to end up somewhere on this axis. And if that was a Cartesian plane, that would be equal to the y-axis, right? So from there, we just have to figure out where 7 pi over 2 lands. We have to figure out if it lands on this side. We just have to see if it lands on this side or that side. And in the case of 7 pi over 2, you can do that by just doing one full rotation, which will bring us back here, because one full rotation, that's equal to 4 pi over 2. And then again, another rotation that gives us 5 pi over 2, and then 6 pi over 2, and then finally 7 pi over 2. So 7 pi over 2 is going to end up on this side of our y-axis, if you will. So this would be 7 pi over 2. And so that's also why sine of 7 pi over 2 is equal to -1 instead of +1. And so with that in mind, now you can see how, since we know that r is going to be the distance from the origin, we're going to end up with just 4 units straight down from the origin, since our angle brings us to somewhere here, and our distance is 4 from the origin, so we'd end up with, like, I guess, like 1, 2, 3, 4 steps down. And then now you can probably more clearly see that if you look at this like a Cartesian plane, this would be equal to the points of 0 and -4, because x is equal to 0, and then we're just going straight down on the y-axis. And so that's the way you can get to this answer without using the formulas. It's a little more tedious, but if the formulas aren't intuitive to you, you can take this approach. So yeah, so the answer to this question is going to be D. Alright, so if the Maclaurin series of the function f of x is the given series here, then the sixth derivative of f evaluated at 0 is equal to what? So this question is kind of just gauging how well you understand how the general formula for a Maclaurin series works. The reason I say this is because it'll make sense in a second. Before I go into it, you might think that maybe to solve this question, you could just reverse this series and turn it back into its original function f of x, and then just take a derivative 6 times and plug in 0. You could do that, and you'd get the right answer, but the computation to get there would be really, really intense. And so there's a better way to do this. And the way to do that is by relating this given series to the general formula for a Maclaurin series. And so to start, let me write out what that is. And so we know that a Maclaurin series is a special case of a Taylor series centered at 0. And so that gives us the formula of f of x would be equal to this summation of the nth derivative of f evaluated at 0 over n factorial times x to the nth power. And so from here, the way we'd relate this to the given series is we could just set this series equal to the general formula of a Maclaurin series. And we can say that this is going to be equal to just this. And then all we'd have to do from here is, well, the question is asking for the sixth derivative of f evaluated at 0. And this is what I was talking about how the formula for Maclaurin series is going to come in handy here. You can see that in the general formula, you can see that there's already an nth derivative of f evaluated at 0, and the question is asking for the sixth derivative. And so what we'd have to do from here is we just have to plug in 6 for n, 6 for n here and here and here and stuff, and in this equation as well, and then just solve for this. Solve for this part of the formula of the Maclaurin series, and we'd have an answer. And so in reality, you don't even have to do any calculus for this question, actually. And so it's going to be, this question is, as a result, it's going to be purely algebra. And so that's nice. And then another thing I'm also going to do is I'm going to rewrite this series in a form that looks more similar to this, and it'll make it more obvious why I'm relating the general formula for a Maclaurin series to the given series. And so when you do that, you should end up with an equality that takes the form of like -1 over n over 3n over n plus 1 times x to the nth power is equal to just the nth derivative of 0 over n factorial times x to the nth power. And now that I've isolated the x of n on both sides, well, for one, these are going to cancel, so it'll make our computation a little bit more easy. But another thing you'll notice is, oh, give me a second. All right, never mind. My computer was having a little bit of a brain fart, so I had to restart it real quick. But anyway, yeah, so now, going back to what I was talking about earlier, now that I've isolated the x of n, x to the nth power on both sides, now you can more clearly see that this term, that's going to be equal to this term here. And so we can say that this would be equal to the nth derivative evaluated at 0 over n factorial. And with that in mind, that's how it'll allow us to just get us to a point where we just have to solve for this term and we'd have an answer. And so from here, all we have to do is plug in 6 for n. So you should end up with an equality that takes the form of -1 to the 6th power over 3 times 6 times 6 plus 6. And then I realized this is supposed to be a 6, not a 1. My bad. And then we'd have the 6th derivative at 0 over 6 factorial times x to the 6th, and then an x to the 6th here as well. And then it's nice because since they're both on this on one side, these x to the 6s are also going to cancel. And so then you'd end up with a simplified equation of just +1 over what this is, and that simplifies, I believe, to 216. Yeah. And then we just have to evaluate what 6 factorial is. And so recall that a factorial, that's just 6 factorial would be equal to 6 times 5 times 4 times 3 times 2 times 1. That's a really, really tedious computation. So if you can, I would suggest also memorizing some of your factorials. If I recall correctly, I believe this is equal to 720. I believe 6 factorial is equal to, yeah, let me double check real quick. So 6 factorial is going to be equal to 720. And so you'd end up with a simplified expression of f to the 6 over 0 over 720. And then from here, all we'd have to do is we just have to isolate, the 6th derivative of f at 0, and you'll end up with our answer. And so when you do that, you should end up with the 6th derivative of f at 0 is going to be equal to 720 over 216. And then all we have to do from there is just simplify this fraction, and we'd have an answer to this question. And I gotta say, this question is this is really evil. Like, these numbers are not fun. There's a lot of simplifications that I have to do, and yeah, wow, these are some ugly numbers. So then this will turn into 316 over the 360 over 108, which turns into 180 over 54, which turns into 90 over 27, and then since these are both multiples of 9, this will ultimately reduce to just 10 over 3. And so this would be the final answer to this question. And so matching that up with our answer choices, the answer to this question would be C. Alright, which one of the following power series equals the given function near the origin? So this question is asking us to convert our function into a power series. And there's a variety of ways you can do that, but each of the approaches, they all involve having to shapeshift your given function into something that kind of looks like a very specific geometric series, which I'll write out. So let's just say we have a target series of that being equal to 1 over 1 minus r. We want to shapeshift this function into something that looks like this. And we know that this is going to be a geometric series, and this specific geometric series is going to be equal to this series from n is equal to 0 to infinity. And actually, I realize this function is in terms of k, so I'll use k instead of n, of just r to the k power. And so once we've managed to shapeshift our function into something that looks like this, then we can convert it into its corresponding series that looks like this series. And so to start, I mentioned that you can do whatever you want to the function, whether that's like adding or subtracting stuff or whatever. You can also take derivatives and integrals to get somewhere, though. That is another valid approach that you can take, and it adds some additional steps that you have to do at the end, but you can still do that. You can still do that. In fact, that's actually going to be the best way to get to progress through this question in this situation. We can actually take an integral of our function here, and that'll get us super close right away to this, and we just have to trim off some stuff later on. So taking an integral, we can say the integral of 1 over x minus 2 squared with respect to x, that's going to be equal to -1 over x minus 2. So you can see right away, just taking that integral got rid of this second power, and we're already getting something that looks kind of like this. The next thing we have to do is we need to rearrange our denominator to look like 1 minus r, because currently it's in the form of x minus 2 instead of 1 minus r. And so that is as simple as we can just rearrange the denominator to look like this. We can just say, we can rearrange it to look like 2 minus x like this, and then flip the sign of the entire fraction. And so after doing this flip, this new function is, I mean, this new fraction is actually equal to this. You can that's a shortcut that you can take. You can flip the signs of this, flip the sign of the 2 and the x, and it turns into positive 2 and negative x, and then flip the entire sign of the function. And then you can see now we're getting closer and closer. All we have to do is we just need to deal with this 2. We need to turn that into a 1. And the way to do that is we can say that this is going to be equal to 1/2 times 1 over 1 minus x over 2. So now you can more clearly see that now we have this fraction in terms of 1 over 1 minus r, where you can clearly see that r is going to be equal to this x over 2. This is going to be our r. And then from there, we can just turn it into a series. So let me clean this up a little bit. I'm going to keep this labeled as r for clarity. And then now we can just turn it into this series, this being equal to the sum from k is equal to 0 to infinity. And then since r is equal to x over 2 in this case, we just have to replace this r with x over 2. So we'd have the series of just x over 2 to the k power. And then also, since we took out a 1/2 here, we're going to also have to keep a 1/2 here as well. And then we can simplify this a little bit, and so this is going to be equal to series k is equal to 0 to infinity, 1/2 times x to the k over 2 to the k, and then we can distribute this 1/2 back into our series. And then this is ultimately going to be equal to this, of x to the k over 2 to the k times 2, which is going to simplify to just 2 to the k plus 1. Now we have a power series. Now all we have to do is we have to take one last step, and we'll have the power series of our function. Recall that I took an integral at the very beginning to get here. And so this power series, even though it's a power series, like it's a valid power series, the problem is it's a power series that's equal to the integral of the function rather than the function itself. And we need a power series of the function itself. And so since we took an integral to get here, all we have to do from here is just take the derivative of this series, and we'll have a valid power series for the function. And so recall that when you're taking the derivative of a series, it follows the same process of just a normal function, except you're just going to attach a sigma term to the end of it once you're done. So taking that derivative with respect to x in this case, because that's our variable, the derivative of our power series k is equal to 0 of x to the k over 2 to the k plus 1, that is going to be equal to this series of k is equal to 0 to infinity of k times x to the k minus 1 over 2 to the k plus 1. And this is going to be the final answer to this question. And so, yeah, so the answer to this question is going to be E. Alright, so if the given series is the Taylor series for f of x is equal to ln of 3x, centered at a is equal to 2, then what is the value of c sub 3? So this question is going to be a little similar to, I don't remember how many questions ago it was, but there was a few questions, a few questions ago that dealt with a series, and we had to relate it to the general formula of a Maclaurin series to get somewhere. So similar to that question, what we're going to have to do to solve this question is, at first you might not really be sure what to do, since we have like an unknown c sub k here, and whatever, yeah, just an unknown c sub k. And the only thing we do know is that f of x is equal to ln of 3x, and it gives us the general form of its Taylor series, but we don't know what c sub k is. And so we're going to have to relate that to the general formula of a Taylor series, and that'll allow us to get somewhere. Now, unfortunately, since we're dealing with a Taylor series and instead of a Maclaurin series, that general formula is going to look a little bit more ugly, because the Maclaurin series is a more simple case of a Taylor series where a would be equal to 0. So to start, let me write out the formula for a Taylor series. So we know that if we wanted to find a Taylor series of f of x, we can say that f of x would be equal to the sum, as k is equal to 0, going to infinity, of the kth derivative of f evaluated at a over k factorial times x minus a to the k power. And so relating that to our case here, in this case, we know that f of x is going to be equal to, or no, let me write this down here. We know that f of x is equal to ln of 3x, and we know that its Taylor series is equal to just this. And so what we're going to have to do from here is we're going to have to relate the given series here to the general formula of the Taylor series. And so in this case, we know that a is equal to 2. And so plugging that into the general formula of the Taylor series, we'd have to say that this is going to be equal to just this, where we have a f, kth derivative of f evaluated at 2 over k factorial times x minus 2 to the k power. And so what you'll notice from here is that both of these terms have an x minus 2 to the k power. And so from here, you can deduce that since we set these equal to each other, we can deduce from here that c sub k is going to be equal to this term. And so you can probably more clearly see that after simplifying things a little bit, we can say that c sub k is going to be equal to f of k. No, the kth derivative of f evaluated at 2 over k factorial. And then the other thing is, for this question, it's only asking us for what c sub 3 is, so we don't have to worry about the rest of the Taylor series formula. So we can, at this point, we can just forget about all this other stuff and just focus on this. And in this case, since it's asking for c sub 3, and we have a relationship between c sub k and this thing, in order to find c sub 3, all we have to do is just plug in 3 for k. And so we'd end up with a new expression that takes the form of c sub 3 is equal to the third derivative of f evaluated at 2 over 3 factorial. And so at this point, all we have to do is we just need to find the third derivative in question and then plug it into this expression and simplify, and we'll have an answer. And we know that f of x is equal to ln of 3x. So to find the third derivative, we just have to differentiate that 3 times. So since we know that f of x is equal to ln of 3x, then f prime of x is going to be equal to just 3 over 3x, which equals 1 over x. And then f double prime of x is going to be equal to negative 1 over x squared. And then f triple prime of x, that's going to be equal to 2 over x cubed, if I'm not mistaken. And so now that we have that third derivative, we just have to plug 2 into said third derivative and then plug it into this expression and simplify. And so when we do that, you should end up with something that looks like 2 over 2 cubed over 3 factorial is going to simplify to 2 over 8 divided by 3 factorial is 3 times 2 times 1, so that's going to be 6. And then this can simplify again to 2 over 8 times 6, which equals 2 over 48, which ultimately equals 1 over 24. And from here, we can say that this is going to be c sub 3. And so yeah, so then we can just compare this with our answer choices. And so the answer to this question is going to be E. Right, so in this question, we're given 3 sequences, and it's asking us to determine whether the sequences are going to be convergent or divergent. So before I start anything with this question, I want to emphasize the fact that we're dealing with a sequence rather than a series. And so that's going to change, and so finding the convergence of or divergence of a sequence is going to be a little different from the case of a series, because the behavior of the convergence of divergence between a sequence and series is not the same. So you couldn't use like series tests on a sequence and get a correct answer. Series tests are only going to work on series. To prove my point, we know that, for example, like the divergence test, if the divergence test of a series is not equal to 0, then the series diverges. But if you use that on a sequence, it's actually going to converge, because if the limit goes to any number that's not like infinity or whatever, then that means that the sequence is going to converge. So with that in mind, checking the convergence or divergence of a sequence is just going to be as straightforward as just taking limits of them and seeing what those limits go to. So starting with the first case, I'll start here. We know that a sub n, that's going to be equal to sine of n over n squared. And then we just have to take a limit of that. So the limit as n approaches infinity of sine of n over n squared. And before I go further, I'm going to start with just focusing on the behavior of solely sine by just putting just a graph just to remind you of the way sine works. So recall that like if you were to graph sine, so like sine of x or something, we know that graph is going to look something like this, where you just have a wave that looks like this, right? Where it's just a constant wave that oscillates between +1 and -1. And so on its own, that would mean that sine is going to be a bounded function, because that means that no matter what the number is, you're always going to end up with something between 1 and -1. And so that would mean that sine of n on its own, if it was a sequence, would diverge, because it's always just going to bounce between 1 and -1 as n approaches infinity. But the thing is, this sequence is actually going to converge because of the fact that it's sine of n divided by n squared. And so that's going to make this series ultimately converge, because similar to the case of it's similar to the process of let's say you take the limit as n approaches infinity of 1 over x. We know that this is going to go to 0 because it's a bottom heavy fraction. That same principle applies to this case, where if you were to graph sine of n over n squared, you'd end up with something that takes the form of something that looks along the lines of this. Something that looks like this, where you'd have that goes something like that on this side, and then something that goes like that on that side. And so you can see in this case of this graph that this is eventually going to go to 0. You can see that this curve, it eventually the wave slowly dies out and eventually just gets closer and closer to just the x-axis of just 0. And so from that you can deduce that this limit is just going to go to 0. And since that limit is a finite number, since it's just going to 0, we can deduce that the first series is going to converge. So I'll label that over here real quick. So we know that this is going to converge. Now we can focus on the second case of b sub n, that being equal to sine of n pi over 2. Now I know right away that this sequence is going to diverge. And the reason why is because, going back to what I mentioned earlier of how sine is a bounded function, notice how our second sequence b sub n is also just sine. It's not sine of x, but it's still just sine. So this is also going to be a bounded function. It's just gonna behave a little differently, but it's still going to stick to the same 3 or 4 numbers. To show you what I mean, I'll even use the first 5 numbers of n to show you what I'm talking about. So with n is equal to 1, you'd end up with sine of pi over 2, which equals 1. In the case of n is equal to 2, you end up with sine of pi. That's going to be equal to 0. In the case of n is equal to 3, you end up with sine of 3 pi over 2, which just goes to -1. And in the case of n is equal to 4, you end up with sine of 2 pi, which goes back to 0. And then at n is equal to 5, you end up going full circle, and you end up back at sine of 5 pi over 2 being equal to 1. And so you can see after every 5 passes of n, you end up going full circle. And so that would mean that this sequence over here, this is just gonna, if I move this over here, or actually no, we don't have to do that. We can get rid of this. You can see from these first 5 passes of n that this sequence, it's just gonna keep bouncing between 1, 0, -1, 0, 1, 0, yada yada yada, so on and so forth. So no matter what n is going to be equal to, b sub n is always going to be equal to 1, 0, or -1. And so with that in mind, it's never going to converge to a single number, which would make it a divergent sequence. And so from that, we can deduce that the second sequence is going to diverge. And so now focusing on the last sequence of c sub n is going to be equal to n sine of 1 over n. Taking that limit, you end up with a limit as n approaches infinity of n sine of 1 over n. And at a first glance, taking that limit might seem a little tricky, but we can use some illegal math here and some shortcuts to approximate this and show that this limit is actually going to converge. I'll show 2 approaches. So I'll show the approach that uses some illegal math, but also another approach that uses some limit identities. So in the first case, we know, like, let's just say, like, some small x, some super tiny x, like 0.001 or whatever, we know that sine of x, that's going to be approximately equal to just x. And so with that in mind, you can turn this into where sine of 1 over n is going to be approximately equal to 1 over n for some small x. And so then you can turn this limit into this illegal limit of the limits as n approaches infinity is going to be equal to n times 1 over n, which just simplifies to 1. Now, if you're not convinced by that, I'll show you a way that you can use this by using some limit properties. So the more proper, precise approach to show that this limit is going to converge is this is also going to be equal to the limit as n approaches 0 of sine of n over n. And then we can use L'Hopital's rule to show that this limit is going to go to 1. And so with that, after doing one pass of L'Hopital's rule, you end up with cosine of n over 1, which just turns into cosine of 0 over 1, which just equals 1. So with either of those two approaches, the illegal approach or the more precise approach, you'll find that the limit is going to go to 1. And since, once again, that limit converges to a specific number, we can say that the third sequence is going to converge. So zooming out a little bit so you can see everything, we find that the first sequence is going to converge, the second sequence is going to diverge, and the third sequence is going to converge. And so the answer to this question, matching that up with our answer choices, is going to be C. Alright, so which type of curve does the polar equation r is equal to 4 secant of theta describe in polar coordinates? So there was another question on this exam that also dealt with a polar curve, where I also conveniently wrote out part of the unit circle and a table. So I did the same thing for this question as well. Oh, excuse me. I did the same thing for this question as well because it's going to be useful. And so yeah, similar to that question, it's like the case of a Cartesian graph where you come up with test values which spits out something else, and then you just connect the dots. Except since we're dealing with a polar graph instead of a Cartesian graph, the coordinates are just going to behave a little differently in like a circular formation. So recall that r, that's going to be your distance from the origin. So I guess like something like this or something. So if you had like a point here, then the r value, yeah, it's just the distance from the origin. And then theta represents the angle of the point, like rotated around this graph like this. And so I've also conveniently wrote out a couple test theta values here that are going to be important for this. Now, there's a reason that I specifically chose these values, because we're dealing with a secant function of, 4 secant of theta. The reason I'm not going beyond pi over 3 is because secant of theta is not defined. It's not defined along this axis. Secant of theta is undefined on like any sort of pi over 2 value. So that's why I'm only going up to pi over 3. And so you can kind of see that it'll make more sense in a second when I start putting in some test values. So starting with 0, you end up with 4 secant of 0, which is going to be equal to 4 times 1 over cosine of 0, which just equals 4 times 1, which just equals 4. So in the case of 4 secant of 0, we're going to end up with an r value that's like approximately, 4 units away from the origin. So you'd end up with something along the Cartesian x-axis, like a point like somewhere around here maybe. And then we can see that that's like 4 units away. And in the case of pi over 6, that's going to be equal to 4 secant of pi over 6, which is equal to 4 times 1 over cosine of pi over 6, which is going to be equal to 4 times 2 over root 3. And then this is going to be greater than 4. And the reason, and this is important. I'm mentioning the fact that it's greater than 4 because what you're going to come to realize is each of the values that I come up with are all going to be greater than 4. So in the next case, we have 4 secant of pi over 4. That's going to be equal to 4 times 2 over root 2, which is going to be greater than our previous value of 4 times 2 over root 3. And then finally, we're going to end up with 4 secant of pi over 3. That's going to be equal to 4 times 2, which is going to be equal to 8. And so each of these values are bigger than the previous one. So starting at the theta is equal to 0 case, in the case of pi over 6, 4 times 2 over root 3, that's going to be like maybe like somewhere around here. And then it's going to angle up. And then once we've accounted for the angle, the theta angle, you're going to find that it's going to be directly above our previous point here. So we're going to have a point here like this. And in the next case, we have 4 times 2 over root 3. Once again, it's going to be even further away from the origin, so like somewhere around here. And then it's going to curve up and end up over here and end up being directly above this point as well. And then once again, same case for the next term. You're going to end up here, and then it's going to rotate up here and end up directly above the previous one. And so when you connect the dots, you'll come to realize that this graph is just going to be a straight line that goes vertically, like this. And so comparing that with the answer choices, the answer to this question is going to be a line. So answer choice E would be the answer to this question. So yeah, so the answer to this question would be E. All right, find the arc length of r is equal to e to the 2 theta, where theta ranges from 0 to 2 pi. So in the case of finding the arc length, just like the case of when you're just dealing with Cartesian coordinates, we're going to have to do some sort of integral. And there is a formula for that. There is a formula for finding the arc length in terms of polar coordinates. And so what that's going to be is that's just going to be the integral from a to b of the square root of r squared plus the derivative of r squared. So just r prime squared. Or I guess a better way to write it would be the derivative of r with respect to theta, so dr d theta squared. And so all we have to do from here is just match this up with the given things here. So in this case, for this question, we know that r is equal to e to the 2 theta. So r is equal to e to the 2 theta. And so dr d theta is going to be equal to 2e to the 2 theta. And then our boundaries are just going to be 0 and 2 pi like given to us here. And so we're going to end up finally with an integral that just takes the form of the integral from 0 to 2 pi of the square root of, the square root of e to the 2 theta squared plus the derivative of r, so 2e 2 theta squared, like so. With respect to theta, that's another thing that I forgot. And so yeah, from here all we have to do is just evaluate this integral. And so then this can simplify to the integral of 0 to 2 pi of e to the 4 theta plus 4e to the 4 theta with respect to theta, which is going to be equal to, that's going to be equal to the integral from 0 to 2 pi of 5 e to the 4 theta. And then from here, we can just isolate this and turn this equal, and then just make this equal to the square root of 5 times the square root of e to the 4 theta, which is going to be equal to the integral of the square root of 5 times e to the 2 theta. And then from here, we can just ultimately take this integral, and then that's going to be equal to the square root of 5 times e to the 2 theta over 2, evaluated from 0 to 2 pi. And so then we just have to plug in the boundaries, and you should end up with something that looks like the square root of 5 over 2 times e to the 2 times 2 pi minus e to the 2 times 0. And then that's just going to simplify to root 5 over 2 times e to the 4 theta minus 1. And so then from here, we can just match it up with our answer choices. And so this is going to be the arc length of the given r function. So matching that up with the answer choices, that's going to be equal to b. Yeah, so the answer to this question is going to be b. All right, so what are the values of p that will make the following series converge? And so, this is interesting. This question is actually verbatim the same as one of the questions on the third midterm from this from spring 2024. So I know right away that the answer is going to be C, but I'll walk through it anyway, in case you didn't see that video. And so in this case, we can see for this series, since we have an n and a p-value, we have to figure out what p is going to be for convergence, like the question says. But also, pretending that this p isn't here for a second, pretending that that's not there for a second. If you don't see that, to find like convergence for a series like this screams to me integral test, because you can see here that ln of n over n, that's actually a really simple integral to do. So for this question, I'm going to use an integral test to get there. And recall that with an integral test, you need to check to make sure that your function is continuous, positive, and non-increasing. Now, I'm putting non-increasing instead of decreasing because there is a major difference between the two. Decreasing means that every following term of the series is strictly less than the other one, whereas a non-increasing series, that allows for the case where you have two terms that are equal to each other, but none of them are going to be greater than each other. And so those are the three conditions that you have to look for with an integral test. And if your series satisfies those three conditions, then you can take an integral test. And the cool thing about the integral test is, I mean, depending on what you're using it on, the computation might be a little ugly. But when it comes to series tests, I like to treat the integral test as like, if series tests are like an arsenal of weapons, then an integral test would be like a nuke, because it's very powerful. I mean, it won't tell you what the series converges to, but whatever the integral says, that's what the series is going to do. And so, yeah, that's why I like to think of it as like a nuke. But anyway, I digress. So this case does, in fact, cover the three cases of continuous, positive, and non-increasing. So then all we have to do is just set up our integral and see if that integral converges. So that integral is going to end up looking something like, your boundaries, you're going to just use, like, the most straightforward case is you can just use the numbers given to us, so 3 and infinity. So in this case, I'm going to use 3 and infinity, which is and nice. And sometimes when you're doing an integral test, you have to change up your lower boundary, because you could end up in a situation where no matter, like, if you have a lower boundary that's too low, you could end up with like an integral test that's going to diverge no matter what, even though you could have a case where it does actually converge. So for example, like in this case, on the previous exam, on midterm 3 that had this question, I believe it was this same question, except it said that n was equal to 1. If I used 1 as the lower boundary, then this integral would diverge no matter what p is. But that was wrong, because that question, like that series did converge depending on what p was. And so I had to change my lower boundary to 2. But thankfully in this case I don't have to do that. I can just set the lower boundary equal to 3 instead. So then we end up with an integral from 3 to infinity of ln of n to the p power over n with respect to n. And this is a very simple integral. We can just take a u sub to get somewhere. So we can say that u is going to be equal to ln of n, and then du is going to be equal to 1 over n dn. So dn is going to be equal to n du. And then adjusting our boundaries, ln of infinity is going to be equal to infinity, and ln of 3 is just ln of 3. So our new boundaries for our integral is going to take the form of the integral from ln of 3 to infinity of u to the p power times n over n du. And then these n's are going to cancel, and we're going to end up with the integral of, from ln of 3 to infinity of just u to the p, which will simplify to u to the p plus 1 over p plus 1, evaluated from ln of 3 to infinity. And yeah, so then when we plug those in, you should end up with something that takes the form of, like, the limit as the limit as u approaches infinity of u to the p plus 1 over p plus 1 minus ln of 3 to the p plus 1 over p plus 1. Now for the remainder of this question, I'm mostly going to be focusing on this limit, because this limit is going to tell us whether or not this series is going to converge, because like the question says, it's asking us to figure out a number for p that will make this converge. And so as you can see in this limit, depending on what p is, this limit can either go to infinity or it can go to 0. Recall that with a limit that goes to infinity, like let's say you have like the limits as like let's say you have the limit as like, I don't know, like x goes to infinity of like x over 1. This is going to go to infinity because it's a top heavy fraction. But in the case of here where we have like the limit as x approaches infinity of like just 1 over x, that's going to go to 0 because it's a bottom heavy fraction. And so applying that to this limit, we have to figure out a number for p that will make this number have a negative exponent. And then when we have a negative exponent, that will allow us to move this u term to the denominator, making it a bottom heavy fraction, thus making that limit go to 0. And so we'd have to say that we need p plus 1 to be less than 0. So we'd have to set up an inequality of p plus 1 has to be less than 0, and then we can simplify this inequality, and we'd come to the conclusion that p would have to be less than negative 1. And so what this inequality tells us is that when p is less than negative, strictly less than, when it's less than negative 1, this limit is going to end up becoming a bottom heavy fraction, which makes it go to 0, thus making the integral converge. And recall that the integral test, that just says that whatever the integral does, that's also what the series does. So if the integral converges, then the series also converges, and if the integral diverges, then the series also diverges. So yeah. And so let me use a test value to prove what I'm talking about. Since we need p to be strictly less than 1, less than negative 1, let's just say p is equal to negative 2. In the case of p is equal to negative 2, then we end up with a limit as u approaches infinity of u of negative 2 plus 1 over negative 2 plus 1, which simplifies to u to the negative 1 over negative 1, which simplifies to 1 over negative 1 times u. And so you can see that we have a bottom heavy fraction, and so this limit would go to 0. And then on the flip side, you can pick another number. We can say, I guess, like p is equal to, I don't know, let's see, I guess we can use negative 1. Or no, I guess we can use, let's use positive 2. In that case, you'd end up with a limit as u approaches infinity of u to the 2 plus 1 over 2 plus 1, which equals u to the 3 over 3, and now we have a top heavy fraction, and so this limit would go to infinity. And so that's why you would need the p-value to be strictly less than negative 1. Because that's what's going to give us a bottom heavy fraction that gives us a convergent limit. And then as for this case over here, like this second term in the integral, that's kind of insignificant relative to, oh, actually, no, I was wrong. No. That is wrong. I should also mention, the reason why it has to be strictly less than negative 1 and not less than or equal to negative 1 is because if you look at the case of where p is equal to negative 1, you're going to end up with two fractions that divide by 0, and you can't divide by 0. And so that's why it has to be strictly less than negative 1. So comparing that with our answer choices, the answer to this question is going to be C. Alright, so what is the area between the spirals of r is equal to theta and r is equal to 2 theta, with theta ranging from 0 to pi over 4? So like the question says, it's just going to be dealing with finding the area of a curve, except it's going to be in polar coordinates instead of Cartesian coordinates. And well, that's because the values are going to be r and theta rather than x and y or something. And then also it tells us that the curves are going to be spirals. So before I go about evaluating this, I'm also going to draw out a little graph here just to give us an idea of the area that we're trying to find. And that should make it easier to visualize, like it'll make more sense why the computation is going to be what it is. And so to start with the first spiral of just r is equal to theta, that's just going to look something like this. Something like that maybe. And then the second spiral of r is equal to 2 theta is just going to be the same thing but bigger. So it's going to spiral out looking like this. And it's asking us to find this area from theta being equal to 0 to theta is equal to pi over 4. And so since we're dealing with polar coordinates, we know that theta, that's going to be the angle rotated around this plane. And so we're going to have to treat this like a unit circle rather than like a Cartesian graph. And so this would be theta is equal to 0. This would be theta is equal to 0. And up here, like somewhere around here, that would be something like theta is equal to pi over 2. And then pi over 4, that ends up smack in the middle of both of those. So we'd end up with like a curve that looks something like this. So this would be theta is equal to pi over 4. And so zooming in on this, we'd be finding an area that looks a little something like this would be like, if I put something here, this would be looking something like this. Something that kind of looks like a horn, I guess. So we'd be trying to find this area. So I'll also shade that over here. Use a different color for that. So yeah, so we'd be finding an area that looks a little something like this. That tiny little thing over there. And so from there, now we can come up with a equation to represent that. And similar to the case of when you're just finding it, the area under the curve in just Cartesian coordinates, you can just take an integral of the function, like just the integral from a to b of f of x or something, and that would give you the area under the curve. Now in the case of polar coordinates, the process of finding an area under the curve, I guess, or within the circle of a polar coordinates system would be a little bit different. The formula for that is going to take the form of where the area would be equal to the integral from a to b of 1/2 r squared with respect to theta, where r squared, that's going to be the function. So either r equals theta or r is equal to 2 theta. Now, similar to the case of when you're finding the area between two curves in Cartesian coordinates, that would look something like the integral from a to b of like f of x minus g of x with respect to x or something like that, right? Now, translating that to polar coordinates, that's going to take the form of a formula that looks like this, where a is going to be equal to the integral from a to b of 1/2 times our first function. I'll just call it r sub 1 theta. R sub 1 squared minus r sub 2 squared with respect to theta, where r sub 1 is going to be the bigger function, and then r sub 2 would be the smaller function, and you'd take the difference between those two. And that's how you'd end up with the area between two curves on a polar coordinate system. The cool thing about this question also is we also don't have to figure out what the boundaries are beforehand, because it tells us that right away. It tells us that theta is going to be from 0 to pi over 4. So for a and b, we can just plug in pi over 4. So the next thing I'm going to do is I'm going to move these equations to the left side here to give myself more space. And so we can say that our equation to find the area in this case, that's just going to be equal to a is going to be equal to the integral from 0 to pi over 4 of 1/2 times 2 theta squared minus theta squared with respect to theta. And then that will simplify to just the integral from pi over 4 of 1/2 times 4 theta squared minus theta squared, which is going to equal 3 theta squared. And so we'll ultimately end up with an integral of just 1/2 3 theta squared. Or yeah, no, I'll just write it out. 4 theta squared minus, if my computer will, there we go. I think my computer's lagging. Oh, there we go. Okay, cool. Theta squared with respect to theta. And then this can ultimately simplify to just the integral from 0 to pi over 4 of 3 theta squared over 2 with respect to theta. And that's going to be a pretty simple integral. That's just going to go to 3 theta cubed over 6, evaluated from 0 to pi over 4. And so then we just have to plug in the boundaries, and so we end up with 3 pi over 4 cubed over 6 minus 0 cubed over 6. And then this term is just going to go to 0, so that's just going to become 0. And so this is ultimately going to turn into 3 times pi cubed over 64 over 6, I believe, minus 0, which would just simplify to 3 pi cubed over 64 times 6, I believe. Yeah, something like that. And then this can simplify to just pi cubed over 64 times 2, which is going to ultimately equal pi cubed over 128. And so this would be the area between the two curves of these two spirals. And so the matching that up with our answer choices, the answer to this question would be B. Right, so in this question, we're going to have to figure out what the interval of convergence is for the given series. And so what that entails is that's similar to the case of when you're just applying a convergence test onto a normal series that's simple and just seeing if it converges or diverges, except the only additional step is that we have another variable that we have to deal with that could change the convergence or divergence of the series depending on what it is. And so we'd have to take a couple of additional steps on top of that. So the initial process is going to be the same. Looking at this series, I think a ratio test would work best here. Usually with questions like this, you're usually going to be using either the ratio test or root test as your initial step. And looking at this series, I think the ratio test would work best here. So recall that the way the ratio test works is you take the limit as n approaches infinity of the absolute value of your series a sub n plus 1 over a sub n. And then if that limit is less than 1, then it converges. If it's greater than 1, then it's going to diverge. And if it's equal to 1, then it's going to be inconclusive. And so since we're looking for the interval of convergence, we're going to want to focus on the condition at which the series is going to converge. And so starting out by computing this limit, we'd end up with a limit that just looks like the limit as n approaches infinity of the absolute value of x minus 2 to the n plus 1 power over n plus 6 divided by x minus 2 to the nth power over n plus 5. And then this will simplify to the absolute value of x minus 2 to the n, just the nth power, no, x minus 2 times n plus 5 over n plus 6. And then this limit is going to evaluate to just the absolute value of x minus 2. You can see this because if you just treat this as like one big constant and then apply L'Hopital's rule once, L'Hopital's rule is going to turn both of these terms into 1. So just and then since we know that this is going to be treated as a constant, all you'd have left is just x minus 2. And then since the ratio test tells us that it's going to converge if the limit is less than 1, we need to set up an inequality where we need to see that the absolute value of x minus 2 has to be less than 1. And since we're dealing with absolute value here, we're going to end up with boundaries at the top and also the bottom. And so what that's going to look like is you're going to end up with an inequality that looks like where x has to be less than 3 and greater than 1. Because let's say, and you can see with these numbers, like if you plug in 1 for this and back into this inequality, you'll end up with the absolute value of -1, which equals 1, which would be inconclusive. And if you plug in 3, you also end up with 1. And so that's why x has to be between 1 and 3. And so now we have our initial boundaries for our series to see if it converges. The next thing we have to do is we have to check the edge cases. So the edge cases would be, in this case, 3 and 1. And even though we know that the series is going to diverge outside of this range, we also need to check to see if it converges or diverges at the edge cases or not. And that's going to determine whether you end up with like a inclusive case or not including that boundary, if that makes sense. So starting with the case of x is equal to 1, you just have to plug that back into the original series. So let's just say x is equal to 1. You end up with a series that looks like n is equal to 0 to infinity of -1 to the n times 1 minus 2 to the nth, which just simplifies to -1 to the nth power over n plus 5. And then this can simplify to just 1. And then you end up with and then you end up with 1 over n plus 5. And now we have a harmonic series. And we know that a harmonic series is going to diverge by default, because after we plugged in 1, we ended up with -1 to the n twice, and that made this series like not an alternating series anymore, because we don't have that -1 to the n power term anymore. And so yeah, so now we have I'll include the intermediate step to make it more obvious. This would simplify to -1 times -1 to the n, which equals n plus 5, and then this top numerator is going to simplify to just 1 over n, which is just 1. So you end up with 1 over n plus 5. And then now you can see that we have a harmonic series, which a harmonic series is going to diverge by default. And so the next case we have to check is going to be x is equal to 3. So starting with the first case, we can start to build our interval. Since we know that the series is going to diverge at 1, we're going to have to exclude the case. So we'd end up with 1 is less than x. And then checking the next case, let's go to x is equal to 3. In that case, plugging that into our series, you should end up with a new series that looks like n is equal to 0 to infinity of -1 to the nth power, and then 3 minus 2, which equals 1. So you'd end up with just 1 to the, or I'll write it out. You end up with 3 minus 2 over n plus 5, and then that's going to simplify to -1 to the nth over n plus 5. And now we have an alternating series. And so since we have an alternating series, we're going to have to also check for conditional convergence. Now, when it comes to an interval of convergence, conditional convergence also counts as convergence. So if we end up with conditional convergence, then we can include the case of x is equal to 3 in our interval of convergence. It doesn't have to converge absolutely. So to start, let's evaluate, since we're dealing with an alternating series now, we're going to have to check the absolute value of the series first. And so taking the absolute value of this series, we end up with just 1 over n plus 5, which gives us the same harmonic series again, which we know is going to diverge. And so now we have to check for conditional convergence, since we found that the absolute value diverged. So the absolute convergence case, that most straightforward case, is not going to happen. So yeah, so we're going to have to check for conditional convergence. And what that entails is we need to check if the series a sub k, if the limits as k approaches, or wait, no, this question is in terms of n, so I'll use n. You have to take the limits as n approaches infinity of a sub n and see if this is equal to 0. And then we also have to see if a sub n is decreasing. And if both of these conditions are met, then the series is going to converge conditionally. So taking the limit, setting up a limit, we can say that the limit as n approaches infinity of 1 over n plus 5, that is in fact going to go to 0 because we have a bottom heavy fraction. So this would be equal to 1 over infinity, which would just equal 0. And so now we just have to check to see if the series is decreasing. And once again, you can tell right away that it is going to be a decreasing series because we have another bottom heavy fraction, because it's just 1 over n plus 5, and while 1 just stays the same. And so so the denominator would continue to get bigger and bigger and bigger, and when you have a bigger denominator, then the fraction just becomes a smaller number. If you're still not convinced, you can also take the derivative of the series, and if that derivative is negative, then you know for sure that it's going to be decreasing. So if I do that, if we take the derivative dn of 1 over n plus 5, you end up with -1 over n plus 5 squared. So we have a negative fraction after taking the derivative, so we know for sure that the limit goes to 0 as n approaches infinity, and we know that the series is also decreasing. And so in the case of x is equal to 3, we know that it's going to converge conditionally. So this series is going to converge conditionally. And since we know that it converges conditionally at x is equal to 3, let me write this down here. Let me also write that this case is going to diverge. And so now we know that at x is equal to 1, it diverges, and then at x is equal to 3, it converges conditionally. And so you'd end up with an interval that looks like 1 is less than x is less than or equal to 3. Because, as I mentioned earlier, with conditional convergence, that still counts as convergence, and so we can still include 3 in our boundary. And so translating this into our answer choices, putting it into the bracket notation, when you just have a less than and not a less than or equal to, that's going to turn into a parenthesis. And then in the case of less than or equal to or greater than or equal to, then that's going to turn into a square bracket. And so this is going to be our interval of convergence for this question. So matching it up with our answer choices, the answer to this question is going to be A. All right, so this question, it's asking us to evaluate the given integral. So looking at this, we're dealing with an improper integral that we're also going to have to split up using a partial fraction decomposition. I know it's improper because, well, the obvious, one of the boundaries, the upper boundary is infinity, but also looking at the denominator, this integral in its current form, I can't really do anything with it, so I'm going to have to split it up a little bit. And so when you do a partial fraction decomposition, the things you have to check for is you have to make sure that the highest power of your numerator is not greater than or equal to the highest power of your denominator. Because if it is, then you're going to have to do long division or polynomial division beforehand and then do your partial fraction decomposition. And then from there you can do it. But the cool thing is in this question we don't have to do that because we just have a 1 in the numerator. And then the denominator, the highest power is 4. And then the next thing you want to do is you want to try to factor out your denominator as much as you can, and then come up with terms for each of the factored out parts. So that's what I'm going to do for here. So looking at this, I can take out an x squared. So we can say that this integral is going to be equal to the integral of 1 over x squared times 1 plus x squared with respect to x. And then once you've factored as much as you can, at this point we can't factor it any further. That's when you can start to do your partial fraction decomposition. And so what that's going to look like in this case, in this first term, we have just an x squared term. And so that's going to be the case of a duplicate case. So what that's going to end up looking like is for our first term, we're just going to end up with a over x. But then for our next term, we're going to have to come up with the same term of b over x, but then increment it by 2. So just b over, or increment it by 1. So the power goes up by 1, so you'd end up with b over x squared. So for example, like if this term was an x cubed, then we'd end up with 3 terms where we'd have an a over x plus b over x squared plus c over x cubed. But we don't have to do that, so I'll get rid of that. And then for our final term, we're going to have to come up with something for this 1 plus x squared thing here. And I mentioned how this thing has already been factored as much as we can. And so we can't split this up, or at least meaningfully split it up into a way to come up with a 2 small simple terms. So we're going to have to come up with one big, more complicated term. So you can see here that we have an x squared as well as a constant attached to it. And so in our numerator, we're going to have to solve for 2 variables. So I'm going to call those c and d. And then another thing is, with each of these constants, since we have 2 terms, one of the constants needs to have an x attached to it. So basically, like in this case, the denominator has an x squared term, and so you have to. And so since the power is a 2, that means we're going to have to come up with 2 terms in our numerator, and then attach an x to each of them. Attach an x to each of these terms, and then lower the power by 1 with each one. So since this is a 2, you end up with 2 terms with an x to 1 power lower, so x squared just becomes x, and then x to the first just becomes x to the 0, which just becomes 1. So you end up with cx plus d. And then similarly, to make it make more sense, like let's say if this was like a 1 plus x cubed, then our numerator would look like cx squared plus bx plus d, or something like that. And so yeah, so now with that out of the way, we have the complete partial fraction decomposition. So our integral is going to look a little something like this. And now we can start to solve for a, b, c, and d. And in order to do that, what you're going to want to do first is you're going to want to multiply all of these terms, by your original integrand's denominator. So I'm going to distribute like a x squared plus x to the 4th to each of these terms. So you'd end up with an expression that looks like x squared plus x to the 4th times 1 over x squared plus x to the 4th is going to be equal to x squared plus x to the 4th times a over x plus b over x squared plus c x plus d over 1 plus x squared. And then when you simplify this, you just end up with 1 is going to be equal to, that's going to be equal to a times x plus x cubed plus b times 1 plus x squared and then plus cx plus d times x squared, I believe. Yeah, something like that. And so yeah, and then from here, all we'd have to do is, let me rewrite this a little bit. This can also be rewritten as, let me split this up a little bit. We can split this into maybe like, just trying to figure out how, like, what would be the most straightforward way to explain this at this point. Because from here, once you have your equation looking like this, there are two primary ways you can go about this to solve for A, B, C, and D. And oh, I know what I can do. Yeah, let me rewrite this as 1 is going to be equal to A times X times 1 plus X squared plus B times 1 plus X squared plus CX plus D times X squared. So from here, the two ways you can go about this is either come up with test values for X that allow like some of these terms to reduce to 0. And what that'll do is that will simplify your expression into something that can allow you to solve for one of these letters one at a time. So looking at the X case, I can get rid of a bunch of stuff initially by first using a test value of X is equal to 0. So in the case of X is equal to 0, we can say that 1 is going to be equal to A times 0 plus B times 1 plus 0 plus C times 0 plus D times 0. And from here, this is going to allow us to cancel out everything except B, and we can find out right away that B, this is going to simplify to just 1 is equal to 0 plus B plus 0 plus 0. And so we can find out right away that B is going to be equal to 1. And then from there, another test value we can use. At this point, I don't think there's anything else we can, I don't think there's any other test values we can use from here. Let's see. Yeah. And so from here, the next thing you'd want to do, since we can't come up with any test values anymore, is you want to relate like terms together. So what I mean by that is I am going to multiply this out and have like an X term attached to each of the letters. And so what that looks like when you distribute everything, you'd end up with an expression that looks like 1 is equal to AX plus AX cubed plus BX squared plus CX cubed plus DX squared. And now to combine like terms, what I mean by that is notice how we have like a AX cubed and a CX cubed here. And so we'd have to say that those two terms would have to be equal to some sort of thing on this side that was also equal to something x cubed, but we don't have an x cubed term on the other side. So we'd be able to say that in this case A plus C would just be equal to 0. And then going down to the next power of x squared, once again on this side we don't have an x squared term, and so once again you'd end up with B plus D is going to be equal to 0. Now moving down to the last variable, we have just an x here, and then we don't know what's, and then once again there's not an x term on this side either, and so you just end up with an expression that looks like A is going to be equal to 0. And then we found out earlier that B is going to be equal to 1, and also you can see that here we have a B by itself as well as just 1. So from here you can also deduce that B is going to be equal to 1. And so from here we have things that we have two variables solved for, and we can solve for C and D. We know that A is equal to 0 as written here, and we know that B is equal to 1. So plugging in 1 for B into this expression, we can find D. So you'd say that 1 plus D is equal to 0, so D would be equal to -1. And then similarly, we know that A is equal to 0, so plugging that into this expression, you'd end up with 0 plus C is equal to 0, which would simplify to C equals 0. And so A is going to be 0, B is going to be 1, C is going to be 0, and D is also going to be -1. And so now that we've done that partial fraction decomposition, we can plug those values back into this integral over here. And so that's going to look like this. I'll move it over here. That's going to look like the integral from 0 to infinity of just 1 over x squared plus negative 1 over 1 plus x squared. And then I can simplify this to just 1 over x squared minus 1 over 1 plus x squared. And then to evaluate this, this integral at first is not that, it might look a little scary, but it's actually not that bad. So the first term, that's just going to go to negative 1 over x. And so this is just going to go to negative 1 over x evaluated from 0 to infinity, or yeah, negative 1 over x evaluated from 0 to infinity. And then this case, that integral is just going to be equal to the tangent inverse of x. If you're, now here's the thing, this is going to be a common case. So I would suggest memorizing that the integral of 1 over 1 plus x squared is equal to the tangent inverse of x. Because if you don't memorize it, then in order to solve this, then you'd have to use a trig substitution, and that's going to be very, very tedious. So I'm just going to say that this is going to be equal to the tangent inverse, the tangent inverse of x. And if you're not sure, I'll go over how to find that manually after solving this question. And so then you'd end up with negative 1 over x minus the tangent inverse of x evaluated from 0 to infinity. And now we can plug in our boundaries. And so that's going to just look like the form of the limits as x approaches infinity of negative 1 over x minus the tangent inverse of x minus just 0 a bunch of times. So that would just look like, wait a minute, I made a mistake. I was wrong. Oh, no. This is not supposed to be 0. The original question had the lower boundary as 1. My bad. Yeah, so this integral is going to be from 1 to infinity, not 0 to infinity. My bad. Like this. So then you'd end up with just minus negative 1 minus the tangent inverse of 1. And so plugging infinity into these terms, we have over here, we have a bottom heavy fraction. So plugging in infinity into that, you're just going to end up with 0. And then the tangent inverse of infinity, that's going to go to pi over 2. So you'd end up with 0 minus pi over 2. And then you'd end up with minus negative 1. And then the tangent inverse of 1, that's going to be pi over 4. And so you'd end up with minus pi over 4. And then you can simplify this and you'd end up with negative pi over 2 plus 1 plus pi over 4, which would ultimately simplify to 1 plus pi over, 1 minus pi over 4. Yeah. And so this would ultimately be the final answer to this question. Yeah, so the answer to this question would be C, I believe, yeah. Alright, so in this question we're just dealing with an indefinite integral, and it's asking us to figure out what that integral is going to be equal to. And you'll probably notice that looking at these answer choices, these all look pretty terrible. And also you'll notice that also each of these answer choices are a series. And so that tells me right away that in its current form, this integral in its current form, we won't be able to integrate it using normal integration techniques. We're going to have to add an additional step beforehand to convert our function into something else that will allow us to use normal integration techniques. And so in that case, what we're going to have to do is we're going to have to convert this series, this integrand into its Maclaurin series. And doing that conversion will allow us to end up with a new term that is actually integrable, I guess. And so the way to do that is usually you want to match up your given function with something that, like, pick a common known Maclaurin series that looks similar to the given function, and then try to manipulate that series into something that ends up being equal to this. And so I see right away that we have an e to the 2x term. So that leads me to believe that I'm going to have to come up with a Maclaurin series that is based off of the general Maclaurin series for e to the x. And if you're wondering where I get this information from, you can find it on the Maclaurin series table for this exam. So to start, we know that the Maclaurin series of e to the x, that's going to be equal to the infinite sum from n is equal to 0 to infinity of x to the n over n factorial. And then when you expand that out, that would be equal to 1 plus x squared over 2 plus x cubed over 6, so on and so forth. Now there's a reason that I wrote out the expansion for the Maclaurin series as well. That's going to be important for later down the line when we're coming up with our series for this question in particular. And so the next step I'm going to do is I'm going to relate this general form to our series. We have an e to the 2x. And notice how in the Maclaurin series for e to the x, we have an x term here and an x term here. And so all we'd have to do for the case of e to the 2x is just replace each of these x's with a 2x instead of an x. And that also includes for the expansion as well. And so as a result, the Maclaurin series for e to the 2x, that's just going to be equal to this sum to infinity of 2x to the n over n factorial, which would be equal to 1 plus 2x plus 2x squared over 2, so on and so forth. And then the next step we're going to do is I'm going to bring this -1 into the mix. And this is the part where, this is the reason why I wrote out the expansion for each of the Maclaurin series as well, because that's important for this. That's how we're going to deal with this -1. So writing that down here, we have the e to the 2x minus 1. And since we know that e to the 2x minus 1, we want to have this term, we want to be able to match it up with our Maclaurin series here. And we know that this Maclaurin series is just simply equal to e to the 2x, right? And so what we'd have to do is we'd have to, since we want this to be equal to this series, the next thing I'm going to do is, instead of writing this series out, I'm going to write out the expansion for this series. And so we'd have to see like something like this. So 1 plus 2x plus 2x squared over 2, yada, yada, yada. And I'm going to put this entire thing in parentheses. So we just have to figure out how to make this equal to this. And the way to do that is, since we have a -1 here, all you have to do to make this equation valid is also to subtract 1 from this side as well. And when you do that, you'll come to realize that this 1 is going to cancel out with this one. And so then these can cancel. And we can say that e to the 2x is going to be minus 1 is just going to be equal to starting with 2x plus 2x squared over 2 plus 2x cubed over 6, yada, yada, yada. And then we can say that that is going to be equal to a series. But since we canceled out the first term in the expansion, we're also going to have to change the starting value of our series. So notice how we had like in this case, we said that our series starts at n is equal to 0. Since we canceled out the very beginning term in our expansion, in this case, we'd have to change that to n is equal to 1, because now we're starting with this term instead. So like this would be n is equal to 0, and then this would be n is equal to 1. And so since we're starting with this term, now we have to say that our series is going to be equal to n is equal to 1 instead of n is equal to 0. And then it's going to also be the same form like this. Because you'll see that it's the case of e to the x minus 1 is still just equal to this case, except we started one term later instead. And then the last step we have to do is we just have to account for this x over here. And that's just as simple as dividing all of these terms by x. And so when you do that, you just end up with e to the 2x minus 1 over x. That's just going to be equal to the series from n is equal to 1 instead of 0 of 2x to the n over n factorial divided by x. And now we have our Maclaurin series, and then from here we can just integrate. But another step I want to do is I just want to simplify this term a little bit. I want to simplify this to make it easier to work with. And so when you do that, I can distribute this n with these two terms. So then this would just become 2 to the n and x over n factorial times x, like so. And then we can cancel out these x terms. And then you just end up with a series that takes the form of this. N is equal to 1 infinity of 2n x to the n minus 1 over n factorial. And now we have our integrand in a form that can be integrated. And so from here, in reality, this integral is actually just going to be equal to this. So we can say that this integral is just going to be equal to the integral, the indefinite integral of our Maclaurin series. With respect to x. And now this integral might look a little scary too, because there's so much stuff going on, but this is actually going to be a really simple integral. We just have to do power rule, reverse power rule once. Because recall that when you're integrating a series, it follows the same rules as when you're just integrating a normal function, except your answer is just going to have a sigma attached to it at the end. And so what I'm going to do is I'm actually just going to rewrite this integral. This is actually just equal to like this, where we have n is equal to 1 to infinity of 2n over n factorial times the integral of just x to the n minus 1. And then all we have to do is just integrate this and then plug it back into this, and we'd end up with our answer. And so now you can probably more clearly see how it's just going to be reverse power rule. And so then this is just going to turn into, that's just going to turn into x to the n over n. And then all we have to do from here is just attach this series back to it, and we have our answer. And so then this is ultimately going to turn into 2n n factorial, and then our summation. And then the last thing we have to do is just add a constant, since we're just doing an indefinite integral. And then this is going to be the final answer to this question. So yeah. And so then we just have to match it up with our answer choices, and so that's going to be E. Right, so which one of the following is the most appropriate substitution for the integral given to us in this question? So while looking at the answer choices and the fact that we have an integral that looks like this, I know right away it's something related to a trig substitution, because you can see all the answer choices have some sort of trig function in them. So to start, in order to go about this, what you'd have to do is you'd have to look at the cases of, you'd have to look for three types of forms in your expression. You'd have to look for something that either looks like a squared plus x squared minus a squared, or a squared minus x squared. And then I'll just put them in radicals here, like so. And in the case of if you see the square root of a squared plus x squared, that would result in a substitution that looks like x is going to be equal to a tangent of theta. And in the case of the square root of x squared minus a squared, that's going to turn into a substitution that looks like x is going to be equal to a secant of theta. And then in the case of a squared minus x squared, that would take the form of x is going to be equal to a sine of theta. And so And so then we'd have to look at our integral and see how this matches up with our three common occurrences here. And at a first glance, it doesn't actually match up with anything. The reason for that is because we're going to have to manipulate this radical a little bit and turn it into something that does look like this. And the way to do that would be by completing the square. And so what that entails is I'm going to be focusing on this part of the expression and turning that into something that takes up like a full quadratic expression that can be factored into two of the same term, because that's what you want to do when you complete the square. If you manage to successfully complete the square, you should end up with a quadratic expression that when you factor it, you can factor it into two identical terms and then square them together, hence the name completing the square. So this, we could end up writing this as like, we have an x squared and we have a 4x there. So what you want to do is you want to pick a number, the same number, one of that where when you add them together, you end up with -4, and then square that number. And so in this case, we know that to add up the same number to get -4, you'd have to add -2 with -2. And so you'd end up with an expression that looks like x squared minus, and then since we know that the number is going to be 2, we also have to square that number. And so you'd end up with x squared minus 4x plus 4, like so. Now the problem is when you complete the squares, you have to make sure that it's equal to, it has to still be equal to our original expression here. And x squared minus 4x plus 4, that's not equal to x squared minus 4x plus 3. So in order to fix that, we just have to add a minus 1 here, and that will make it equal to it. Because when you simplify this, you'll end up back with this. And so this is going to be a successful completion of the square. And so when you factor this, you'll see that this is going to factor to x minus 2 times x minus 2 minus 1. And so this is what I was talking about, how where you want to come up with a new quadratic expression that when you factor it, you end up with the same term twice. And so now that we've done that, then you can simplify this again to just x minus 2 squared minus 1, and then put the radical back in. And so now that we've completed the square, now you can probably see that this expression is going to look more similar to one of the cases over here. And so this is going to match up the closest with the case of, this is going to match up the closest with this case of x squared minus a squared. The reason why is because our x term is here and we're subtracting it by 1. So you can clearly see that a is going to be equal to 1 because, well, this would be a squared, and then this would be x squared. And so a squared would be equal to 1, and then take the square root of that and you just end up with 1 again. And so yeah, and so we know from that a is going to be equal to 1. And then now all we have to do is plug these values into our substitution. And so since we're dealing with the secant case, you'd end up with a substitution that takes the form of x is equal to 1 secant of theta. However, there is one additional step that we also have to take. We are not done here yet because you can see here that the substitution here, it tells us that x, it tells us that x is equal to a secant of theta. But in this case, we're dealing with the x minus 2 term, which is not x. And so what we'd have to do is that would be as simple as just replacing this with x minus 2, and then just moving this 2 to the other side of the expression, and then that will make this, it'll make the substitution valid. And so then you just end up with a new substitution that just looks like x is equal to 1 secant of theta plus 2, because all I did was just move the negative 2 to the other side. And so yeah, and so now we have our completed substitution. And so this is going to be the substitution. And so matching this up with the answer choices, you should end up with answer choice C. Okay, so which of the following polar coordinates describe the points 2 root 3 and 2 in Cartesian coordinates? So for a question like this, we're just, to go about this question, it would just be a matter of converting the given polar coordinates back to Cartesian using the conversion formulas between polar and Cartesian. And so we know that in the case of like a Cartesian coordinate plane, you have just the terms of x and y, right? And then in polar coordinates, that's going to turn into r and theta. And so, so you'd have like r and then theta like this, as opposed to x and y. And then the conversion formulas, and then we just have to convert between these two. And so the conversion formulas between Cartesian and polar are going to look something like where x, that's going to be equal to r cosine of theta, and y is going to be equal to r sine of theta. So to go about this question, it would just be as simple as just plugging in each of these terms into these formulas, and then it'll spit out something that will be in Cartesian, and we'll just see if that's going to be equal to this case over here. So starting with the first case, we have 4 and pi over 6. So I'll put that over here. In the case of 4 and pi over 6, x is going to be equal to, and then also I should also label that this is going to be r and that's going to be theta. So then x would be equal to 4 cosine of pi over 6. And then that's going to equal 4 times root 3 over 2, which just equals 2 root 3. And then for y, then you'd end up with y is going to be equal to 4 sine of pi over 6. And then that's going to be equal to 4 times 1/2, which equals 2. So when we combine this back into our coordinate plane, this is going to turn into just 2 root 3 and 2, which does in fact match up with our our target here. So we can say that the first choice is going to describe the point 2 root 3 and 2 in Cartesian coordinates. Now, part of the reason why you can have multiple different polar coordinates that describe the same thing in Cartesian is because, as you remember probably, polar coordinates behaves in like a circular pattern and like a radial pattern rather than Cartesian, where it can just be anywhere on the plane. And so since it's going to be going in circles over and over again, you could just end up having repetitive points after you do one full rotation around, say, a unit circle. Speaking of the unit circle, that's going to be very important for anything related to polar coordinates. So I would suggest memorizing it, and or at least at the very least being able to understand the unit circle very well for questions like this. And so moving on to the second point, we have -4 and -11 pi over 6. So plugging that into our formulas, you end up with x is going to be equal to -4 times cosine of -11 pi over 6. And like this. And so since we're dealing with a negative theta value, that's going to be a counterclockwise rotation around the polar coordinate system. And so -11 pi over 6, that's going to be the same thing as just positive pi over 6. And so this is going to equal -4 times root 3 over 2. And then we know that that's going to be equal to -2 root 3. And so we know right away that x is not equal to this point here, so we don't even have to compute y. So we know right away that 2 is not going to be, it's not going to describe the point that we want in Cartesian. So 2 is out of the question here. Now for the third case, we just have to look at, we have -4 and 7 pi over 6. So plugging that into our conversion formulas, you'd have that x is going to be equal to -4 cosine of 7 pi over 6. And 7 pi over 6, that is going to be equal to -1. That's good. That's going to be a little bit over half a rotation, half a clockwise, or no, half a counterclockwise rotation around the unit circle. So then this would be equal to -4 times -1. -4 times negative root 3 over 2, which is going to be equal to 2 over root 3. So our x coordinate does match up with our target. Now going over to the y case, we have y is going to be equal to -4 sine of 7 pi over 6, which is going to be equal to -4 times -1/2. And so that's going to be equal to 2. And so the third case as well, plugging that back into a Cartesian coordinate, you end up with 2 root 3 and 2. And so yeah, so that means that the third case is also going to describe the point that we want. And so that means that answer choice, or no, so the first coordinate and the third coordinate are going to match up, but not the second one. So matching that up with our answer choices, the answer to this question would be B. Oh, and then also I think I said that I got to correct myself. I also mentioned that that is going to be just under a full rotation counterclockwise. I meant to say that's clockwise. It's going to be clockwise around the unit circle, and then that equals pi over 6. But yeah, so the answer to this question is going to be B. All right, so in this question, we're going to be dealing with some physical applications. So this is going to be a little interesting. So this question, it's also going to gauge how well you understand physics too. So that's going to be interesting. A cubic tank, we're given a cubic tank whose sides are 1 meter long, and it sits on the ground and is filled with a liquid of density 1200 kilograms per cubic meter. If we take the gravitational acceleration of g is equal to 10 meters per second squared, compute the work in joules necessary to empty the tank by pumping the liquid through its top. Oh wow, so this question is using g is equal to 10? Oh man, I'm sure that's going to piss off a bunch of physicists and maybe some physics majors too. Because I know some of my professors from some of the physics classes that I've taken they've been so hell-bent on not using g equals 10 and always using something like 9.81 or something. But I digress. Okay, let's get through this. Let's get through this question. So to start, I'm going to visualize what our system is going to look like. So it says that we have a cubic tank whose sides are 1 meter long. And so you'd end up with something that looks like this, or this would be our tank. And then since it's a cube, each side is going to be 1 meter long. And then the next thing I'm going to do is I'm going to convert this into a two-dimensional visualization where we just have a tank like this, where the height of it is going to be 1 meter, and then it has like liquid in it. And so I'm going to be focusing mostly on the height for this because that's going to be the biggest determining factor in how we're going to solve this question. Since we know that the tank is a cube, that means that the height is also going to be 1 meter since it says each side is 1 meter. And then the next thing I'm going to do is I'm going to look at some of the equations that we're going to need to work with. So the question is asking us to compute the work. And we know that work is going to be equal to force times distance. And then we know that force, that's going to be equal to mass times acceleration. And then it also gives us a density, that being that rho is equal to 1200 kilograms per cubic meter. And then we know that we also know that density, that's going to be equal to mass divided by volume. This is also going to be important because we need to isolate, we need to extract mass from the density so that we can plug it into our force equation and ultimately plug it into our work equation to come up with an answer. And we know that the density of the liquid is 1200 kilograms per cubic meter. And also we know that that would mean that also, since we're dealing with a cubic tank that is 1 cubic meter, we can say that the volume is also going to be 1 cubic meter. So I'm just going to put V is equal to 1 here. And so that's going to make our job of extracting mass pretty easy, because then from here we can just say that 1200 is equal to m over 1, which means that the mass is going to be equal to 1200 kilograms as well. And so now that we have a mass, we can plug that back into this equation. And so then we can say that F is going to be equal to, that is going to be equal to 1200 times some acceleration. And the acceleration that we're going to be using is we're going to be using the gravitational acceleration given to us as g equals 10. And so I'm going to plug in g here, which is going to give us 10, which would mean that force is going to be equal to 12,000. And now the reason why we're using the gravitational acceleration is because we know that the tank was filled with liquid, and so the liquid is going down because of gravity. So the gravity is going to be the only force in the case of this question. And so, and it's asking us to compute the work necessary to empty the tank, pumping the liquid through its top. So it's asking us how much work would it take to undo that process of undoing the gravity and stuff. And so now, moving on to our work equation, we know that work is equal to force times distance. So moving that over here, we have to say that work is going to be equal to 12,000 times some distance. And this is where things are going to start to get a little interesting, because the distance is not going to be a constant. It's actually going to change depending on how much liquid is in the tank at any given time. Emphasis on at any given time. That means that we're going to end up dealing with some sort of differential, anything like rate of change related, because let's say the tank is completely filled up with water or whatever liquid we're dealing with. So let's just say let's say that it's completely filled up with water. So at the very beginning, the distance to pump the water out is going to be 0 meters because it's filled to the very brim. So the distance that the liquid has to travel upwards is going to be 0. But as you take out more and more liquid, that distance is going to increase, because now the liquid has to travel more distance to get out of the tank, because it's going upwards now. So it has to go like that way. And so with that in mind, we can actually model the distance that we need to travel as just d is going to be equal to d is going to be equal to 1 minus, let's just say y. I'll use y. D is going to be equal to 1 minus y. I'm using y because we're going to have to travel upwards. So like on a axis, that would be like, I guess, like the y-axis. And we're starting with 1 because 1 is going to be the maximum height, because it says that the tank is 1 meter tall. And then y is going to change depending on how much liquid is in the tank at any given time. And so that's why also the next thing we're going to have to do is we're going to have to also attach a differential to our distance and put a dy here. And then from here, now we can set up our work equation. And we're going to end up with an integral. We're going to end up with work is going to be equal to the integral from 0 to 1 of 12,000 times 1 minus y with respect to y. And the reason we're integrating from 0 to 1 is because we know that the 0 to 1 is going to be our interval, because we know that the maximum height is going to be 1 meter and the minimum height is going to be 0 meters. And then y can just change anywhere in between, depending on how much liquid is in the tank at any given moment in time. And so that's why our work equation is going to look like this integral. So now that we have this integral, now we can evaluate this. And so this is going to simplify to the integral from 0 to 1 of 12,000 minus 12,000 y. And then that's going to just turn into 12,000 y minus 6,000 y squared, evaluated from 0 to 1. And then plugging in the boundaries, that's just going to turn into 12,000 times 1 minus 6,000 times 1. And then the lower boundary is 0, so it's going to become a bunch of zeros after that. And so then this can simplify to just 12,000 minus 6,000, which is just going to equal 6,000. And so this is ultimately going to be the total amount of work needed to pump the liquid out of the tank. So matching that up with our answer choices, the answer to this question is going to be A. Okay, so given that the natural log of 1 plus x is equal to this given series, then find the smallest number of terms of the series we need to add to compute the value of the natural log of 1.1 with an error of less than or equal to 10 to the negative 8. So in this question, I can see that, well, we have a natural log and it's equating it to a series. This series happens to be the Maclaurin series of the natural log of x. And also coincidentally, this Maclaurin series also has a negative 1 to the n power term attached to it, so that's going to be indicative of an alternating series. And then the question is also asking us to find the smallest number of terms of the series that we would need to add together to compute the value of this within some error threshold here. So it would be safe to assume that we're dealing with a question where we'd have to take advantage of the alternating series estimation theorem to get somewhere. And so recall what that's going to be is the alternating series estimation theorem states with this equation that the partial sum, let's just say the absolute value of s minus s sub n, that's going to be equal to the absolute value of the latest term of some series, let's just say a sub n plus 1. And then the alternating series estimation theorem says that this latest term is going to be either less than or equal to some error threshold depending on the conditions of the problem. So in this case, we're dealing with it where it wants it to be strictly less than or equal to some error threshold here. And so we can say that the absolute value of a sub n sub plus 1 would have to be less than or equal to 10 to the negative 8. And so from here, the next step is just to come up with a term for a sub n plus 1. To start, I'm going to denote our original series as just a sub n. And then from here, you can deduce that the absolute value of a sub n plus 1 would just end up being x to the n plus 1 over n plus 1. And having it in an absolute value allows us to eliminate this negative 1 thing in our computation. And so then this expression is going to turn into x to the n plus 1 over n plus 1 is going to be less than or equal to 10 to the negative 8. And so from here, now that we have this inequality, now we can start working towards coming up with a number for n, because n is going to represent the number of terms in the series. And the question wants us to find the smallest number of those terms to compute the requested value here by the Purdue Math Department of the natural log of 1.1. So we'd have to we'd have to come up with the smallest number, so a smallest number n that would allow us to satisfy this question. Now there is one additional problem that we have to worry about. Unlike normal cases of questions like this, usually the only unknown you have would be n, and so it would just be as simple as solving for n in this inequality. But in this question, we have another unknown value, that being x here. So we have to figure out what x is going to be. And thankfully, we can do that because this question also gives us this natural log value. We can use this to come up with an x value, because usually in questions like this, it just tells you like what's the smallest number of terms that you'd have to add up to get within some threshold, but it doesn't ask for a specific number, whereas this question does, that being the natural log of 1.1. So yeah, so from here we just have to set up an equation saying that we're given the natural log of 1 plus x right here, as well as the natural log of 1.1. So we can just set these equal to each other and then solve for x. So we can just say that the natural log of 1 plus x would be equal to the natural log of 1.1. And then we can simplify this again and have just 1 plus x equals 1.1, ultimately giving us that x would be equal to 0.1. And so, excuse me, and so from there, we've already gotten rid of one of the unknowns. We can just plug in 0.1 for x over here, and so that would give us a new inequality saying that 0.1 to the n plus 1 power over n plus 1 has to be less than or equal to 10 to the negative 8. And then from here, now we can solve for n. And there's a couple ways you can do that. You can try to figure out how to do this algebraically and end up with an n value. Another way you can do this also is for questions like this, it would actually be viable to guess and check. And so to start, what I'm gonna do is, for this question, I'd say that the easiest approach would be to guess and check. We'd have to come up with a couple of like trial numbers for n, and when we plug in those n values, see if it satisfies this inequality here. And so for this question, hopefully we probably only have to guess and check about 4 times. The way to do that is usually a good number to start with for the guess and check approach would be to start with usually like the highest answer choice of the question here. So in this case, that would be 9. Not to mention, another reason I'd say 9 is a good number to start with is because we want to satisfy the inequality where it has to be less than 10 to the negative 8. And so if you were to plug in 9 into this expression, n plus 1 would be equal to 10, which is pretty close to negative 8. So my initial guessing number is close to the exponent of our threshold here. So I'll start with that. So starting with n is equal to 9, you're going to end up with 0.1 times n plus 1, and n is 9, so you'd end up with, or I'll just write it out, so 9 plus 1 over 9 plus 1, which would equal 0.1 to the 10th power over 10. And then this can be rewritten, because it's 0.1, that can be rewritten as 1 over 10 to the 10th power over 10, which would then simplify to 10 to the negative 10 over 10. And then we know that this, because it's a negative 10 is less than negative 8. And so we know that this term, in the case of n is equal to 9, we do satisfy this inequality. And so what this tells us is that 9 terms is going to be enough terms that we need to add up to end up with an approximate value for the natural log of 1.1 being less than or equal to our threshold value. The problem is there is a good chance that we can go lower because it's asking for the smallest number of terms. So from here, since after we started with 9, all we have to do from here is just go down. So the next number in the process would be n is equal to 8. So in that case, when n is equal to 8, you end up with 0.1 to the 9th power over 9, which going back to, if you look at the pattern of the way I simplified this over here, we can go straight to simplifying this to just 10 to the negative 9 over 9, which is also going to be less than 10 to the negative 8, because 10 to the negative 9 is always going to be less than 10 to the negative 8. And so n equals 8 also satisfies the conditions of this question. So 8 terms would be enough to have like an accurate enough approximation, but I do think we can go even lower. Not to mention 8 isn't even an answer choice. So again, going to our next lowest number of n is equal to 7, same process, rinse and repeat, 0.1 to the 8th power over 8. That simplifies to 10 to the negative 8 over 8, which once again, this is also going to be less than 10 to the negative 8 because it's a fraction. So even though this exponent is the same as this exponent, since it's going to be a fraction, it's going to end up being less. But now I think we've hit our limit, because from here, I think if we go down to n is equal to 6, it's not going to satisfy the inequality. And so to prove it, I'll even use it. I'll even put in n is equal to 6. So in the case of n is equal to 6, you end up with 0.1 to the 7th over 7, which simplifies to 10 to the negative 7 over 7. And this is not going to be less than this. This is actually going to be greater than or equal to 10 to the negative 8. And so I've just proven from here that 6 terms is not going to be enough terms to come up with an accurate enough approximation, which would mean that n equals 7, so 7 terms would be the lowest number of terms that we'd need to add together to end up with an approximation that's accurate enough for this question. And so in this case, n is equal to 7 would be enough to satisfy this equation. And so the answer to this question, matching that up with our answer choices, would be D.